So while we're waiting for people to come, how many of you watched the tutorial from last year on YouTube? How many of you felt that the audio quality was bad? Okay, so you were the one who was posting those comments? I'm joking. There were so many funny comments on the audio quality, and honestly, it was fair. None of us were YouTuber. So when we created the video, we just mostly paid attention to quality of the video. We never realized that actually audio quality is not that great. And I think it was mostly my microphone that wasn't that great. So we uploaded the video and we realized that actually a lot of people complain about the audio quality, and they said that, oh, can you please use diffusion model to improve the audio quality? Can you do something about that? So funny thing is that a couple of weeks ago, I actually caught my wife doing a lot of derivations. There were like pages of derivations of elbow. And I said, oh, are you doing diffusion models now? Are you like writing she does machine learning for medical imaging and stuff. I said, are you trying to derive the objective of like diffusion models for with elbow and stuff? She said, yeah, I want to pick up this area. I want to try it for my data. And I said, why don't you watch my YouTube video? It's really cool. We go over all of it. She said, audio quality is very bad, Arash. So yes, we lost a lot of audience last year for audio quality. So this year we're going to try. That's why we're trying to make sure that everything's set up properly, and hopefully the Zoom folks can hear us very well, and we can have a good recording for future maybe YouTube videos or something. I'm going to wait for 1 more minute. I guess maybe we can start. Is that good? Okay. Awesome. Thank you everyone for being here. And sorry that we have a small room. I don't think this year the rooms are big. My name is Arash Wadat. I'm a senior research manager at NVIDIA Research. And today I will be joining Jiaming Song, research scientist at NVIDIA, as well as Chenling Meng, last year PhD student at Stanford, who will be joining us online today. And we're very, very excited to share this tutorial with you, which we call it Denoising Diffusion Models, a generative learning Big Bang. And we have a really good reason why we call it this way. The fact that you're here, you're probably familiar with deep generative learning. Just to remind you what we do in deep generative learning. In this space, we assume that we have a collection of samples drawn from a data distribution. If we are, for example, working on images, this data distribution might be just distribution of cat images. And what we do, we use this collection of samples to train a deep neural network. Hopefully, if everything goes well, this deep neural network can capture the true data distribution from those samples, at the test time, we can start drawing new samples using that deep neural network and generate new samples that look like the training data distribution. So if we are working with cats, hopefully we can generate cute, handsome cat images. Generative learning has many applications ranging from for example, art and design, content generation, representation learning, and gaming and entertainment. And we're seeing a lot of now new use cases. And the fact that the term generative AI is becoming very popular, we're seeing a lot of interest now in industry on applying these techniques for various applications. If you are working with deep generative learning and you look at the landscape of deep generative learning, you're going to see that this landscape is filled with so many different frameworks, right? At the very end, the old techniques like restricted Boltzmann machine, Bayesian networks, and as you come closer, you see VAEs, normalizing flows, energy-based models, and at the forefront, you may see generative adversarial networks, autoregressive models that are heavily used for language models, and denoising diffusion models, which is the topic of this tutorial. When we were thinking about the name of this tutorial, we thought that maybe it's fair to say that denoising diffusion models are a new deep generative learning Big Bang. So I don't come from cosmology background. I just know a tiny bit that there's one of the theories of explaining like what's happening with universe is that universe alternates between these like phases of expansion and contraction. And between each one of these like phases, there's a Big Bang happening that basically kind of give birth to a new universe. So we're not cosmologists. We don't know cosmology that much, but we've been around at CVPR and we know CVPR. So we said, okay, let's look at the data and see what's happening with deep generative learning at CVPR. And we just went manually downloaded CVPR papers the papers one by one, but the pages one by one. And we run some simple just search to see how many CVPR papers were published with titles like GANs, generative adversarial networks, and diffusion models. And we're seeing this trend here, where we're seeing currently that probably around 2018-19 was a very popular time for GANs at CVPR, even though GANs were becoming popular at like other venues like ICLR. I think original GAN, DC GAN, and progressive GAN came actually at ICLR, but gradually CVPR community also picked up this space, and we saw really amazing work in that space. And again, something similar is happening with diffusion models, where some of the early works like DDPM guided diffusion came at ICLR, ICML, and we're gradually seeing now CVPR community picking up this space as well. And this year specifically, there are 100 papers at CVPR with title diffusion on it. Our statistics can be biased because we're just looking at the titles when we were doing this histogram. So even though that we may not know anything, we're just seeing that there's a contraction expansion happening in the topic, and it seems that there's a new big bang happening on generative learning for visual domain at least, and there are new papers and interests emerging on this space. So today we're gonna have 3 sessions. I'm doing the first part where I'm gonna talk about the fundamentals, including training, sampling, acceleration, and guidance. And later, Chenlin will talk about applications of diffusion models on images, including architecture design, editing, personalization, fine-tuning, and low-level vision. And later at the end, Jiaming will talk about other applications of diffusion models in other domains, including inverse problems, video, 3D, and large content generation. And we're going to have 15 minutes of break in between these sessions. We're going to be posting these slides on this website you're seeing in the bottom, and hopefully we can have a high quality video with a good audio, and we can post those on that website. Before starting, I just want to have a disclaimer. This field is growing really fast with the speed of light, and even like most of us are having really hard time with catching up with everything. So there's no way we could review all the papers that are happening and being published in this space. So if there's a paper that you really care about and you felt bad that we didn't include in this tutorial, please just let us know, send us a friendly email, and we'll try to include in the next version of this tutorial, hopefully, if you have any. But it's just very hard for us also to keep up with everything that's happening out there. I want to just also make one acknowledgement that because the first part is mostly about fundamentals, some of the slides that I would be using were actually used in the last tutorial in 2022, and most of these slides were built by me, Karsten, and Ruchi. So I want to give credit to these 2 fellows who put a lot of effort making these slides, and I'm taking liberty and using some of those. Because this year program, this fundamental aspect is very short compared to now the new things that have been happening in this space. So if you're interested in knowing about these fundamental maybe aspects in more detail, we probably had a bit better treatment maybe at some point in the previous version of this workshop. So feel free to check that one as well. So let's start with the first segment, fundamentals, training, sampling, acceleration, and guidance. I'm gonna split today's session, my part of the talk into 4 parts. I'm gonna start with denoising diffusion probabilistic models, or DDPMs. Then I will continue with the score-based generative modeling with differential equations, and then we'll talk about accelerated sampling and conditional generation and guidance. So let's start with the first part, denoising diffusion probabilistic models. So denoising diffusion models officially consist of 2 processes. So we have a forward process that is shown here from left to right. We're gonna use my cat's picture, Peanut, which was taken in Vancouver actually maybe like 10 years ago or something. So we take his picture, and in the forward process, we just add noise gradually to this image. And we do it many times in so many steps that eventually on the right side, we converge to pure noise. So the forward process is just simply a perturbation process that starts from an image and keeps adding noise so many times that such that eventually we converge to a known distribution. And in this case, it's going to be a normal distribution with known mean and variance. The reverse process is the reverse of this process. So it starts from noise and it tries to generate data by iterative denoising. So here, forward process is from left to right, and the reverse process from right to left. And it's actually the reverse process that is the one that we're most interested in, because it's a generative process that starts from noise and generates data. So diving deep into these processes, in the forward process, we're going to assume that we have this process in T steps. T is just number of steps. At every step, we're going to assume that we're going to generate a sample given the previous sample with some normal distribution. So we're going to just generate x1 given x0, x2 given x1, x3 given x2. And at every step, as I said, we're going to use just a simple normal distribution where we sample from xt given xt minus 1. And here, this distribution has very simple mean and a standard deviation. The mean of this distribution over xt is the same as xt minus 1 with some rescaling in front. So you can think of this beta t as just very small scalar close to 0. And you basically, if beta t is very close to 0, this 1 minus beta t is almost like close to 1. So you basically take this xt minus 1, you scale it tiny bit down, and then you add a bit of noise that has the standard variance of beta t, right? So you basically take xt minus 1, scale it down, add a bit of noise, then again scale it down, add a bit of noise, right? So this forward process is defined with this normal conditional. Given each one of these conditionals, now we can define a joint distribution on all the samples generated on the trajectories. So this joint distribution will be the product of all the conditionals here. And this simply basically will form the joint distribution of all the samples starting from x1 all the way to xt. Remember that I was saying that the forward process generates one image at a time, but sometimes we may want to just generate a particular step given the initial samples. Given that we're using a normal distribution in the forward process, we can easily show that you can marginalize out intermediate steps and directly generate, for example, x4 given the initial sample. So for that, we will need some definition. So let's just define alpha bar t as product of these betas that we discussed in the previous slide. This is just a definition. And now we can use this alpha bar t to define the diffusion kernel that generates sample at time step t given initial sample using this normal distribution again. And this will have a very simple like mean, which is again some rescale version of the input image and some noise with a variance 1 minus alpha bar t, right? So the nice thing about working with normal distributions is that you can easily generate intermediate steps, samples from intermediate steps given the input image. So for sampling, remember that we can always use reparameterization trick, right? So if you want to generate sample xt, you can you want to basically generate sample from this normal distribution. You can express that sampling using this reparameterization trick. Here we have just a mean from this normal distribution, and we have a standard deviation times this epsilon, where epsilon is just a random sample generated from a standard normal distribution. I want to emphasize that these beta t values plays a key role here. We're going to use the term noise schedule to refer to the beta t values. Ideally, we want to design this forward process, these beta t values, such that alpha bar t, this alpha bar at the end of the process, approaches to 0. And the reason we want this is that if alpha bar t approaches to 0, we know that the distribution of x at the end of this process will also converge to a standard normal distribution. And this is something we will need later for sample generation. So you basically, if you plug this 0 to here, you're going to see that you have standard normal distribution at the end. So we talked about the process and what happens to like individual like samples. Let's talk about what happens to the distribution of samples, right? Let's talk about like the marginal distribution of the samples at that particular like, time step t. To define that, we need this like, we need to look into this diffuse data distribution, and to get this, we basically need to look at the joint distribution of clean samples and these perturbed samples. And this joint simply can be decomposed into distribution of the data samples, input data, and this diffusion kernel that generates noisy samples given x0, right? So we know this is a particular normal distribution, and this is just some input data distribution, right? If we visualize this for some toy 1D data set, so we see that this is like our 1D toy data set where we have this like PDF of x0. So this is kind of, you take a PDF and you rotate it, right? So this is some data distribution. As you go in the forward process, the marginal data distribution at those time steps will look like something like this. So what's happening here is that you can see that as we are diffusing the data distribution, the distribution of data at these time steps becomes smoother and smoother, right, as you go forward. And it becomes smoother such that eventually it becomes just a standard normal distribution. You can actually show that mathematically forward process is some form of applying a Gaussian convolution to the input data distribution, right? This is like convolution in a sense of like signal processing. When you apply Gaussian convolution, your signal becomes smooth. And something like that's happening in the distribution level. Your distribution is becoming smoother and smoother. We should also note that we usually don't have this input data distribution in closed form. We don't have access to this PDF. And as a result, we also don't have access to these intermediate distributions, right? It is just for only toy example that we can visualize. In reality, in practice, we only have samples from base training data distribution, and using the diffusion kernel, we can just not generate samples from intermediate distribution. We never have access to the PDFs. We only have access to samples. So now that we talked about forward process, the question is, how can we generate data, right? And you can imagine now that we have this forward process, maybe we can just start from the end and come backward towards data distribution to generate data. And this is basically what the denoising process does. Recall that I said we designed the forward process such that at the end of the diffusion process, the distribution of the diffused data gets to standard normal, right? So now we're going to assume that data at the end of process has just a standard normal, and we're going to sample from this denoising distribution that generates xt minus 1 given xt, right? So this tries to generate the denoised version of xt given the current state. So you can see that in order to generate data, all we need to learn is this denoising model. So now the question is, how can we approximate this denoising model? And the answer is that actually you can approximate this denoising model using a normal distribution, assuming that in the forward process, beta t values are small per step. So if in the forward process, you have a small amount of noise injection, you can show that mathematically the denoising model is also a normal distribution with usually the same, let's say, standard deviation. So this is really useful because now we can use just normal distribution to represent these denoising models. So inspired by that, we're going to now define this reverse denoising process that, as I said, is going to start from noise and it's going to learn to generate data by denoising. At every step, we're going to use a normal distribution to denoise input images. Here we have this the definition of reverse process. So we first assume that at the end, the distribution of the samples is just standard normal. At every step, we use this normal distribution that infers the mean and some standard deviation. And this actually, the main part is actually this mean part that represent the average denoised image. Like given this xt, think of xt some like noisy image. This is just a neural network that will predict what is the xt minus 1 in average. How does it look like, right? And this is the main trainable component. And because it takes just a noisy image and it predicts the average version of less noisier version of that image, this mu has the same input and output size. If you have an image, you're basically predicting some like less noisy version of that image. So usually we use UNets or denoising autoencoders to represent this mu here. Given this definition of now distributions, we can use them to define the joint distribution over the whole trajectory. So we basically just use a product of these conditionals as well as the space distribution. Now that we talk about forward process and reverse process, we need to come up with a way to train this denoising model, right? It turns out that as my wife was doing, you can just use elbow to derive the training objective. Elbow, or the variational bond, is the objective that is typically used for training VAEs. This variational bond is basically a bond on the marginal likelihood that our model gives to a data distribution. So here we're going to assume QX0 is the data distribution. We're not going to go to the derivation. We're going to just have in mind that recall that XT can be generated using reparameterization trick. One of these early works by Jonathan Ho et al. At NeurIPS 2020 realized that if you assume that your mean, this mean of the denoising model, is parameterized with something like this. So think of these just some weight, just some scaling in front of XT is the noisy input, minus some, again, scaling in front of this network, epsilon theta. This is kind of a reparameterization trick where in order to form this the mean of the denoising distribution, you're going to just use XT minus some scalar times a neural network, and again, some scaling. So they had a very good reason. They looked at the structure of this objective and they saw that there are terms like this. And by using this parameterization, basically they could get much simpler objective, training objective. So they show that using this parameterization, you can just do some simple mathematical steps. And from this variational bond, you can get to very simple objective where you have now expectation over data samples generated from training data distribution, samples like from the diffusion step. So you kind of generate a random sample from like uniform distribution over all the diffusion steps. You generate this epsilon, which is just some standard normal distribution. And using this, you just generate a diffuse sample. So here, what we are seeing, diffuse sample. So here we have diffuse sample, and then we are training this epsilon theta network, and we train it by regressing to the noise that was used to generate the original noisy image, right? So we basically, I don't know how to clean this actually. I don't know what I did. Sorry. Okay. So basically what we are doing here, we just diffuse a sample and we train a network to predict the noise that was used for creating that diffuse sample. So we're going to use this network, we call it noise prediction network, because it takes a noisy instance and try to predict the noise that was used for generating that perturbed instance. Yeah. Maybe not, if you don't mind. Yeah, I'm sorry if I'm losing you now. Yeah, maybe at the end of this section I can stop if. So one thing that I'm skipping here is this epsilon, this lambda t is some weighting of this term over time steps, and Jonathan Ho et al. Observed that basically you, if you drop this weighting, or equally if you just set this weight to 1, you can you will get much simpler objective that also works really well in practice. Like this, by training this like objective without this weighting, you get high quality samples. Just to summarize, the training algorithm looks like something like this. You generate, you draw samples from data distribution. This is like basically a mini batch of training data. You randomly sample a diffusion step. You randomly sample basically a vector from standard normal distribution. You use that vector to generate a perturbed sample, a diffuse sample, and you train a neural network, this noise prediction neural network, to predict the noise that was used. And given that, after training, if you have this epsilon theta, you can now start generating samples by first drawing samples from the terminal distribution, standard normal, by walking backward on this process. This is basically a reverse process. At every step, what we are doing, we're sampling from the reverse denoising basically distribution. And this, what we have here is just a mean. And here we have just some noise injected. This is basically a parameterization trick. We have mean plus standard deviation times this is standard normal distribution. So we iteratively basically can generate samples by going over these steps. I will skip this. This might be a good time for me to stop and let maybe like 1 or 2 questions. Would you like?
Yes, if you can go one slide back, what is not here, I never seen this one before. So what is not here is that the network of this training depends on the time step for us.
Yes, true.
How does this depend? Because how does this dependence enter the network? Is it different network for each time step?
No, so we're gonna actually, that's exactly the slide that I jumped. So now we can discuss it. So I thought this is, maybe I shouldn't spend. So you're right. We are sharing network, and there is a time. No, it's totally fine. No, I think you got the idea. Okay, it's a shared network basically. Short version. Yeah.
Training to inject noise in the inference process. Like, I get the part in the training, right?
Yeah.
It's actually kind of common training to like add a lot of noise, right?
Yeah.
And then like in inference time, you try to remove it.
So the noise that you talk about, is it the noise injected here, for example, like I think for generation? So we're going to in fact see a variant of this that we're not going to have noise there anymore. So it's going to be only just a deterministic mapping. And actually there's one work by Jiaming that we're going to mention, that how we can do this, convert these models to deterministic mappings. In the interest of time, I will go forward and I will make sure that maybe we stop briefly at the end of each section, but we're going to make sure that we can do a Q&A at the end, hopefully. Okay, sorry. Let me start with this second part, score-based generative modeling with differential equations. So, not many of us may remember differential equations. To be honest, myself, like I had to go back and read some textbook when I started doing diffusion models. Let's just do a 1-slide crash course on differential equations. On the left side, you see ordinary differential equations, and think of them as like some system where you have this like this state variable, or you can think of this image. Where you can think of this as a function where this is a function of time, but you don't have this function closed form. What you have is just the update rule of this function. You basically know how this function is evolving as time evolves, as a function of time, right? This actually happens in a lot of domain, like in different scientific domains, where you're working with problems where you don't have the access to the functions in closed form, but you know how these functions are evolving over time. So differential equations basically represent these functions, or the derivative of this function with respect to time, with some other function, right? So here we have this x, like some one-dimensional variable, and we have this time. And in order to basically construct x, you can, sorry, let me make sure you can see my laser. So in order to construct this x, what we can do, we can basically, this f represents some form of like vector field, and you can start from some initial point and follow this vector field to get some deterministic trajectories. And you can get those by just solving this ODE using this basically by just simply integrating f starting from some x0. So you can just get xt by x0 plus this integral of f from 0 to t. It happens that in many cases, we actually cannot solve this integral analytically. So what we do, actually, we end up using some numerical techniques to find xt's on these trajectories iteratively using like our current xt. We just simply use some linear approximation of this function locally to get the next xt. And we keep just updating this xt to get the full trajectory. So there is something called neural ODEs, where you have these variables where the update rule of these variables are represented by a neural network, and we're going to see some of those later. Then on the other side, we have also stochastic differential equations that are actually a little bit more complicated. In stochastic differential equations, not only we have this now deterministic update rule, we also have this stochastic component that injects some form of noise to this update. So in this context, this deterministic component, we're going to call it drift coefficient. It basically has very similar role as this F here, but then we have this now stochastic component with this scalar, for example, coefficient sigma, that you can think of it just some like scalar that determines how much noise we're going to inject. It's usually called diffusion coefficient. And we have this omega t, which represent Wiener processes. You can think of this in a very hand-wavy way. You can think of this omega t as some like independent Gaussian noise injected at each time step, right? So this basically represents all the stochasticity that comes into system at every step. And now you basically want to see how a system will evolve when you have this deterministic component and this stochastic component. If you want to solve SDEs, you can do again similar updates, like iterative updates, where you use current xt, again similar linear approximation of this integral here locally, and then you have this additional term that basically draws a sample from a standard normal distribution and rescales it with this diffusion coefficient and the square root of the step size, right? So this is where now noise injection will happen, and then at every update you actually have some random noise injection happening into that update. So as a result, if you just draw these trajectories, they will look like some random walk in this space of X, and if you do this many times, you're going to have these like different random walks over time. Because of this noise injection, these trajectories will be different every time that you're running them. So in a seminal work by Song et al. At ICLR 2021, the authors showed that, in fact, the forward process that we just discussed in the previous part can be considered as a discretization of a particular stochastic differential equation. So they show that if you take this forward process, either, for example, consider a limit where t is infinity, or just basically write down, and you can see that this basically normal distribution is solving this SDE at every step. Now, this is really cool because we can now start working with directly SDEs rather than these like discrete time diffusion models. So you can think of these SDEs as the continuous time version of these DDPMs that we discussed in the previous section. So just to see how these forward processes look like, we have in this side now this one-dimensional data distribution where, like, if you draw samples, you will see some like maybe cat images, and we start from a sample here and we diffuse using this forward SDE, and each trajectory shows like one particular like, forward process. Remember that we have these two terms. We have this drift term and diffusion term. You can think of these like two terms as like the first term is forget about the scalar. So you have this minus xt. So you can think of this term is always pointing towards origin. So anytime that you're trying to update, there's this force that pushes you towards origin, and then you have this diffusion term that tries to push you away. It adds actually dispersion. And what happens is that these two terms are balanced such that at the end of process, you basically know that your samples will come, the distribution of samples would converge to the standard normal distribution, right? So there are these two forces that eventually it equilibrates, and at the end you get a standard normal distribution. This is exactly the same thing. This is basically the continuous version of the process, continuous time version of the process we discussed in the previous part. So now that we have a SDE that basically perturbs data, the question is, how can we generate data? How can we now learn to generate data? And the answer is basically the same as before. We just need to learn how to undo this process, start from base distribution, the normal distribution, and walk back towards data distribution. So there is this classical actually result in SDE literature that shows that if you have this forward process, and if you want to just not define the reverse process, all you need to have access to is the logarithmic derivative of the distribution of data at that time step, right? So this derivative of log qt xt with respect to xt, we're going to call it the score function. Think of this like, this basic qt is the diffuse data distribution at time step t. We just need the logarithmic derivative of that with respect to xt. Right? We're going to just call this score function in this talk. So you can see that All the other terms are the same. We only need this score function. So the problem of generation simply just boils down, how can we estimate this score function? So, sorry, this is we covered. So how can we get this score function? The simplest thing we could do maybe is just say, oh, I'm going to just form a neural network. And then I'm going to just generate these two expectations, try to generate samples at these like different time steps, right? I'm going to just diffuse data distribution. These two expectations just generate samples at different time steps. And I'm going to have a neural network and try to regress that neural network to the score function of data, right? This is really cool if we could do. The problem is that we don't have access to it. You remember, like at the beginning, I was talking about, we can always sample from Qt. We never have Qt in closed form, and we never have this score function in closed form. So even though this is a well-defined objective, this is actually this is Fisher divergence, and you can show that you're actually learning a well-defined statistical model. Unfortunately, we never have access to this term score function. So there is another classical result from Vincent in 2011, shows that we can sidestep this with another method called denoising score matching. So recall that we had this like diffusion kernel that generates xt given x0 in the discrete time setting. We can exactly come up, we can also derive the same diffusion kernel for the forward, the continuous time forward processes. So we can write down this diffusion kernel. It's going to be a very simple normal distribution, believe me, with some like well-defined coefficients. This is basically the same thing that we saw in the, very similar to what we saw in the first part. And we have access to this diffusion kernel. It's a very simple normal distribution. And this classical result says that rather than regressing our neural network to the marginal data distribution at that step, remember, like we were just doing the score function of data distribution at xt, what we can do, we can regress our neural network to the score function of this diffusion kernel. And the nice thing about this diffusion kernel is that we actually have it closed form. We can compute it very easily. And this classical result says that in expectation, if you minimize this regression loss, you can mathematically show that this objective will be minimum when your S theta, your neural network that's trying to approximate the score function, matches the score function of data. So this is really cool. We can just try to regress to this diffusion, the score function of diffusion kernel, and learn a score function through this. And what is really also nice about this is that if you now just simply plug in this normal distribution, do a few steps, you're going to see that the objective that emerges is exactly the same objective that we saw in the previous part. So this basically shows that the previous part that we talked about, you can actually write down the denoising score matching objective by just manipulating the variational bond. You can just write down the variational bond, do some manipulation, and you're going to get this like denoising score matching objective that was also derived, can be derived also from a completely different perspective. So the another nice thing about this is that given that both discrete time diffusion and continuous time diffusion are training basically the same objective, you can actually convert one to another. So if you train, for example, discrete time diffusion models, as long as the number of steps is very large, you can easily convert it to continuous time diffusion models, and vice versa. If you have continuous time diffusion model, you can just discretize it and get discrete time diffusion models. In general, how to parameterize model and how to reweight this objective. So remember, there's weighting here that plays a key role. This weighting mechanism, parameterization, these two play a key role in the quality of the results we get. I would encourage you to check this paper from our colleagues at NVIDIA, who actually got also Best Paper Award at NeurIPS 2022, where they discuss all these different design decisions that play a key role in diffusion models. Now we're going to get to the deterministic part that I promised a bit earlier. On the left side, you're seeing the trajectories that are generated as you're solving the generative SDE, right? But this again, seminal work by Song et al. At ICR 2021, they actually also observe that you can take these SDEs and convert them to an ODE, right? These ODs are shown here on the right side. So the structure of these ODs have very similar form as the SDEs that we see in the generation. The nice thing about these ODs is that now you can actually train a score function by just, like the same objective, the denoising score matching objective. At the sampling time, now you can use ODEs to generate samples. So this is actually where you can remove all the stochasticity at the steps that earlier I was asked, and you can basically now generate like samples in the base distribution and convert them to samples in the data distribution using some deterministic mappings. And this is only possible because of the continuous time formulation. Basically, by switching to continuous time formulation, we can now convert SDEs to ODs and solve these ODs. There are a few advantages in sampling using ODEs. One thing is that ODEs have been around for a very long time. There are many advanced solvers, so it's much easier to accelerate ODEs using some advanced solvers, advanced numerical techniques. Also, ODEs provide a deterministic mapping between input noise and output generated image. And this deterministic mapping sometimes is helpful. For example, when you have some application where you want to do like image manipulation and stuff, this deterministic mapping is needed to just take images, map them to noise, and then come back to the image space. Additionally, these ODEs can be considered as a particular form of neural ODEs, and we actually have a rich literature where we know how we can compute log likelihood of the data distribution under the trained model. So we can actually use now these like deterministic ODE formulation to measure the log likelihood that our model gives to a data samples, for example, on the validation set or test data. So it's very helpful to know how well, for example, our model does in terms of like mode coverage and log likelihood estimation. I can take maybe like a minute break and let you ask maybe one or two questions. Are there any questions here?
So the use of a normal distribution, like, is that helpful over, say, a uniform distribution?
That's a good question. So one reason why we like uniform distribution is that we can easily marginalize out intermediate steps and stuff. So there's really simple expressions for that. For uniform, I actually don't know if the marginalization will be easy. The other problem with uniform is that because you have such limited range, sometimes you want to have like full support in the data distribution and stuff. I'm not sure if uniform would provide that necessarily, but there is some work like where they try to replace normal with the gamma distribution, different like form of distribution. In practice, I don't know how much it changes performance. And there are also some work that completely abandons like noise injection and argue that maybe we don't need even noise. Yeah.
I didn't get how you jump from stochastic from the SDE or the another assumption, or there was some derivation?
So there's some derivation that I'm completely hiding, and so you can basically take this SD and solve a Fokker-Planck equation, and you will get this ODE. The main feature of these ODEs is that I maybe didn't mention this. So the distribution of these trajectories at every time step is same as distribution of these stochastic trajectories. So you can show that, and as a result, basically you're basically sampling from the same distribution using these ODEs under some assumptions. Yeah.
To numerically solve ODE, I should on every time stamp around neural network.
Exactly. That is the problem. That's the computational complex of these models. Yeah. Okay, I'll move forward, and now that you asked me about sampling, let's talk about how we can accelerate sampling from diffusion models. So when we started doing actually these diffusion models, we realized that there are three criteria that are really hard to satisfy with almost any generative model, especially on images. And these three criteria are fast sampling, mode coverage, and high quality sample generation. So if you look at GANs, for example, they tend to generate very high quality samples very rapidly. If you look at like VAEs or normalizing flows, by definition, they have very good mode coverage. they can generate samples fast usually, but they often suffer from poor sample quality. And then you have diffusion models that their objective is by definition is defined such that they have very good mode coverage. We're seeing really high quality samples generated by them, but because of this iterative procedure that we just talked about, and because at every step you're calling a neural network, sample generation from diffusion models can be really slow. And this actually limits some of the use cases that you could have in, like, for example, real-time interactive applications. So at this part, we're trying to see if we can, whether we can tackle the generative, we call this generative learning trilemma, the fact that none of these models can address all three criteria at the same time. So here we're going to try to see, can we tackle this trilemma by just accelerating diffusion models, right? So we know diffusion models are doing well on these two dimensions, so can we make them also fast? So the techniques in this space can be grouped into four categories. I'm going to go over each one of them one by one. So let's start with advanced ODE or SDE solvers. So remember that, again, there is this deterministic ODEs that map base normal distribution to data distribution, right? And this is a very simple version of them, where you have this update where you're using epsilon theta network to update X. One of the simplest things we can do is that we can use simply just Euler method, which approximates these trajectories locally with some linear function, right? This linear function can be used basically at this point. We can just use now the locally linear approximation of this function and update the sample with some step size. And as you can see here, the moment you try to take large denoising step, this linear approximation will diverge from, will kind of have error with respect to the ground truth trajectory. Actually, this person sitting here, Jiaming, was one of the first people who showed that with the correct parameterization of data space and parameterization of time, in fact, these first order Euler methods can do really well in practice, assuming that you have right basic scaling of time and right scaling of data variables. But nevertheless, in the past couple of years, we've seen works where they try to build on top of this and have basically higher order approximation of this function locally. So we have seen methods like RK4, multi-stepping, and Hume method that basically, in a nutshell, what they're trying to do, they're trying to approximate this OD trajectory with higher order, basically, for example, polynomials, so that they have better approximation and lower numerical errors. So in fact, the research in this space has been growing very rapidly. There has been many different ODE solvers. So I actually personally don't have even technical background to go over them one by one. But the nice about these ODE solver is that most of them are plug and play. So if you have just a function that you want to integrate, you can just plug into these solvers and use these solvers to generate samples from them. And these solvers tend to be better than something Euler discretization and earlier works, for example, DDPM sampling technique. This brings me to second part, distillation techniques. Remember that, again, in the ODE sampling, we have a deterministic mapping from some XT. Think of like XT, some sample generated at a particular time step, and another sample generated on the same trajectory later on, right? So there's a deterministic mapping between these two. So you may ask me, all right, how can we just train neural networks to directly predict this XT prime given the current XT, right? So given this deterministic mapping, if we have enough expressivity, a neural network should be able to directly predict this XT minus XT prime given XT. So, in fact, one of the works that came in this space called progressive distillation tries to do something like this. The basic idea of progressive distillation is that imagine that you have a solver that generates these trajectories, and you can call this solver twice to get two updates. And you can use the output of these two updates to train another neural network to approximate those two updates. So the basic idea is that you basically form a student, and this student tries to learn what teacher would do in 2 steps. And the task of a student is to predict the same output in only one function call. So you basically, if you have like 4 steps, next time after one distillation state, your student will be able to solve the same problem in only 2 steps, and the next step you can do it in 1 step, right? So you can see that iteratively you can start from many steps, which is what ODE solvers do, and progressively distill it to students who can solve now this ODE with lower and lower number of functions. And eventually you can get to 1 step. In fact, Chen-Lin, who will be also talking next after me, showed that by using this technique, progressive distillation, in latent space, which we'll talk a bit later, you can get these diffusion models that can generate very high quality samples in only 2 steps. And she will be talking about, this paper will be present at CVPR 2023 this week, and it's also one of the candidates for best paper. So I would definitely encourage you to check it out. Another work that emerged in this space recently is a method called consistency distillation. Again, remember that on ODE trajectories, we have this deterministic mapping between noise and all the samples generated on the trajectory all the way back to a clean image, right? So the basic idea of this consistent distillation is that if you have a neural network, we're going to call it F theta, if the task of this neural network is to predict clean image, given this noisy image at a particular time step, this neural network should have the same prediction for all the time steps, right? Because we know all these samples on the OD trajectories are going to be mapped to the same clean image. So in consistent distillation, the idea is that if you have a neural network that is predicting these X0s, all of them should predict the same X0. So they basically use this consistency distillation idea to train this F theta. So the basic idea is you need to generate XT and XT prime. Think of like just 2 samples on the same trajectory. And the way you can do this, you can, for example, sample from XT. So you can just diffuse a data, like training data sample, and you can solve ODE between T and T prime, for example, and you will get XT and XT prime. Now that you have 2 samples on the same trajectory, you will basically train F with this objective function here. And what this objective function does is you basically use F using the exponential moving average parameters at XT. So XT, remember, is here, it's the smaller step. And this is basically your teacher, and your student is F at the larger step, right? So you're basically distilling this exponential moving average, your teacher, to the network itself at larger step. So you can think of this, probably this F that use exponential moving average, it will have gradually better and better approximation of X0 for small t's, and you're going to gradually be able to distill this knowledge to larger t's, like larger F values. So gradually this function starts building like better like reconstruction of X0, and you propagate that information to the next step, and eventually they show that if this objective is 0, then basically your F is predicting X0s on this trajectory. So this was about the distillation ideas on ODEs. And you can ask me, what about SDEs? Can we do any distillation on SDEs? Remember that in SDEs, we no longer have deterministic mapping between samples, right? So if you if you have at particular step XT and you want to predict XT prime, all you can do, you can just actually infer a distribution over this less noisy version of images. So you cannot actually have a deterministic mapping, but you can talk about the distribution of less noisy images. And it turns out that this distribution can be normal distribution only when you're denoising for a small step, right? As we saw in the first part. The moment your XT and XT prime are far from each other, you no longer can use simple distribution. You have to use multimodal complex distributions. So there are 2 papers, one from us actually, and one from Ruchi Go, and we show that we can actually use GANs or energy-based models to approximate these denoising models. And when you do this now, you won't need many denoising steps. You can reduce the number of denoising steps because you have more complex distributions that are mimicking this denoising distribution. There are also additional works that I'm not going to cover in this space on distillation techniques. So if you're interested in this topic, I would encourage you to check these papers here. And this brings me to low dimensional diffusion models. So this is the third category of methods that are used for accelerating sampling from diffusion models. So one of the simplest things that we could do if we want to generate data is that, for example, if we're working with images, we could just generate low resolution version of that image and later just super resolve it to generate high resolution version of this, right? So this is basically the idea of cascaded generation, where you start from low resolution image and then you generate that, and then later you generate a high resolution, and then given that you generate a higher resolution version. And this is the idea that was used actually at the core of DALL-E 2, Imagine, as well as Edify from NVIDIA. Another idea is rather than training diffusion models directly in the data space, what you can do, you can use something like autoencoders or variable autoencoders to map your data to some latent space and train diffusion models on that latent embedding of the input data, right? So here, the idea of latent diffusion model is that you use some autoencoder or VAE, you take these input data samples, you map them using some encoders to a latent space, and then you use a decoder to map latent embeddings back to data space, and then you train diffusion models directly on the latent embedding of data. So this is very simple. Now, rather than training diffusion directly on very high resolution for some images, you can map them to some smaller resolution and train diffusion models there. We actually proposed this a while ago, and back then we did envision 3 advantages for latent diffusion models that we listed actually in the original paper. One of the main advantages of latent diffusion model is that because this autoencoder maps the data to a distribution that is close to normal distribution, you know that this distribution of encodings is going to be a simple, smooth distribution. The moment you have this, like you're training diffusion models on some smooth distributions, you know that these SDEs that will emerge in the latent space are going to be also smoother and simpler to solve. You know, like if you have very highly multimodal data, these SDEs can be also complex. But if you're mapping to some space that is very well defined and smooth, you know that these SDEs will be also smoother, and it's going to be easier to solve them numerically. Another advantage of latent diffusion model is that by going to latent space, you actually introduce expressivity and flexibility into your model. We know that if, for example, if you add the dimensionality of data, your generative model will be more expressive. On the other side, if you, for example, compress the data, then your diffusion model will be defined in much smaller space, and maybe it will be easier to train it on some training data. And finally, there are some data types like graph, text, or 3D data where defining diffusion models directly on that type of data is very challenging, and you can just simply take data and diffuse it. But if in that type of data you have access to some autoencoders, you can basically map the data to some latent space and learn diffusion models on top of latent embeddings of data. And actually, we're seeing many works in this space that are emerging, especially for 3D data, to use latent diffusion models. In the original paper, we actually we proposed end-to-end training of latent diffusion models using variable autoencoders. And one of our key technical contributions was that we showed how we can optimize the cross-entropy term, basically using just denoising score matching objective. So I'm not going to go to details of this objective, just have in mind that basically we can train latent diffusion models end-to-end by training both autoencoder and latent diffusion model at the same time. Later on, Rombach et al. Actually did a seminal work on latent diffusion models that you're probably more familiar with, that started also stable diffusion. One of their main design decision was that rather than training the system end-to-end, let's train them in 2 stages. And this way you first train the autoencoder and then later you train the diffusion prior. The nice thing about this is that it's actually scalable, it's easier, like you kind of train autoencoders and then you fix it and then you train the diffusion model in the prior, and you have actually less number of neural networks to deal with at the same time. Also, they focused heavily on compressing data, which is really cool. They basically use advanced autoencoders and adversarial training to take input images and map them to as small as possible latent space. And therefore, the diffusion model that they were training in that latent space didn't have to be very big. And this also showed that you can actually not scale this up to data sets like Lion and other large data set. And in fact, they also showed that the expressivity of latent diffusion was on many exciting conditional problems that you probably have noticed. So in general, the efficiency and expressivity of the latent diffusion models and plus open source access of stable diffusion have fueled a large body of work in the community that you're probably seeing now at this conference. A lot of amazing works are coming with stable diffusion. If you're interested in training, like learning about more about like low dimensional diffusion models, I would also encourage you to check out these papers. In the interest of time, I will jump just directly to the final part, which is conditional generation and guidance. So in many applications, you don't just want to generate any data. You basically want to have some fine-grained control into that generation process, right? So this is usually done by training conditional models, for example, text-to-image conditional models or any like layout conditional models. So we don't want to just necessarily generate any images. We want to have some control over that generative process. So in this part, I'm going to talk about how we can have that kind of control over generation. So conditioning or guidance techniques can be grouped into these three categories. Let me just start directly with the explicit conditioning. In explicit conditioning, the goal is to train a conditional model that would generate, let's say, random variable x given y. Y is just input conditioning. It's like some text, and then x is just a sample that you want to generate. It's just, for example, image in the text-to-image case. And you can show that you can basically just modify the training objective we've seen so far and train conditional diffusion models, right? The only modification is that now, rather than only sampling X from data distribution, we're going to sample pairs of X and their input conditioning. And then we're going to basically pass that input conditioning to the neural network that is learning to denoise image, or this epsilon prediction network will take not only noisy image, it will also take input conditioning. And you can show that by doing this, you're basically learning a diffusion model for this conditional X given Y. If you have a neural network that previously was taking only XT, these noisy images, what's going to happen is that now your neural network will also take additional input, which is this input conditioning. And it will use that additional input to predict the noise that was used to generate this XT. So this is just a simple explicit conditional models training. And this is like one way of doing it. The second category of groups is called classifier guidance. So remember that if you want to generate from a conditional model like this X given Y, all you need to have is just the score function of XT given Y, right? So remember, when we want to generate P of samples from P of X, we needed just a score function of P of XT. But now if you want to generate samples from this conditional, all you need is just a score function of XT given Y. So let's just try a very simple Bayesian rule just to see how we can compute this score function of conditional. So we have this score function of conditional. We have just Bayes rule here. So we express this condition as P of Y given XT times P of XT divided by PY. You should note that this PY does not depend on XT. So this basically, when you're taking derivative, you can ignore this term. So this score function simply becomes just the sum of this score function and this one. And if you check it carefully, you will see that this is just simply a score function of data on the, like, for example, images. And this is the gradient, classifier gradient, that this, you can think of P of Y given XT. If like Y is just some categorical variables, you can form this using just a classifier, and you can take the gradient of the output of this classifier with respect to XT to get this term. So the idea of classifier guidance is that if you have some diffusion model on some domain, let's say images, and now you want to guide the sampling generation, all you need to do is just to train a classifier that predicts the labels you're interested in given the noisy images. And by just taking the gradient of this classifier, you can provide guidance to the generation. Now, if you're doing this, you may want to also control the influence of, sorry, I will wrap up You may want to also control the influence of the classifier, and then you can introduce this like guidance scalar that is just some scale in front of this classifier gradient. And the basic idea is that you can think of this guidance scalar equivalent to some like temperature introduced into this classifier term. And you're basically using this W, you can tune the influence of the classifier. That's classifier guidance. In classifier free guidance, now we want to come up with the approach where we can maybe get rid of also classifier. Instead of training classifier, we want to see if we can do something else. Again, we can go back to the base rule, and I'm just showing you the same base rule we did previously. I just rearranged terms. Remember, in classifier guidance, we need this gradient, but now this gradient can be also expressed as the difference of these two score functions. And this score function here is the unconditional diffusion model. So this term has no conditioning. So remember, this is just basically a score function or diffusion model trained on images. This is a conditional score function, and it is very easy to train. If you have some like labels, you can just train a conditional score function as we saw earlier. So the idea of classifier free guidance is to, instead of classifier gradient, they actually use two diffusion models, one conditional, one unconditional, to form this term, right? So what they do, the basic idea of classifier free guidance is just train, you can share these two models. You can just train one model that is trained to do both conditional diffusion model and also unconditional. The only little trick is that when you're training this model jointly, sometimes when you're training unconditional, you will drop the conditioning and you pass something like a null embedding or null input. So you can just train one model to capture these two. And once you have, you can just plug it, like rather than classifier guidance, you can just plug this into classifier guidance and you're going to get a very simple expression. So I'm not going to go over this. So because we're running out of time, so sorry that it was fast, but we went over 4 parts. We talked about discrete time diffusion models. We talked about how we can take discrete time diffusion models and convert them to continuous time diffusion models. And then we talked about accelerated sampling from diffusion models. And then I talked about guidance and conditioning. We're gonna soon have a break. And then after break, Chenling and Jiami will talk about a lot of exciting application and use cases of diffusion models. In a very selfish way, I want to just very quickly say, we're hiring. If you are interested in this space, just find my tweet and maybe apply via these links. I really appreciate your time, and I don't want to keep folks, so we can end the session so you guys can have maybe 10 minutes of break. Please be back at 10:15, and I will be here to answer any questions. Thanks a lot. So you can get up and walk. It's okay. I will be here to answer any questions that you may have.
Oh, okay, cool. So hello, everyone. Welcome to the CVPR 2023 diffusion model tutorial. I'm Chenling from Stanford University, and this is a joint tutorial with Jiaming and Arash from NVIDIA. So in this section, we'll be talking about applications of denoising diffusion models on images. So here is an outline of the topics we're going to cover in this session. So first, we're going to talk about diffusion model architectures. And then we'll move on to image editing and customization techniques of diffusion models. And finally, we're going to wrap up this session with other applications of diffusion models, including image classification and adversarial robustness. So before we get started, we'd like to thank everyone for their contribution to our tutorial. So last month, Jiaming sent out a Twitter post asking the community to recommend papers, since there are like so many amazing papers on the relevant topics. We actually got so many suggestive feedback from the community, and we actually list all of the feedbacks here on this website. However, due to the time constraint, we're only able to cover part of the papers on the list. So if you're interested in learning more about these topics, we strongly recommend you checking out these papers on the GitHub repo. And here's the link to it. And thank you again for everyone's contribution to our tutorial. So cool, so let's get started. So the first topic I'm gonna talk about is diffusion model architecture. So unit architecture is a very powerful architecture commonly used for computer vision tasks. It consists of a contracting path and an expansive path as shown here, which actually gives it the U-shaped architecture. UNet is perhaps one of the most commonly seen architecture backbones for large-scale image-based diffusion models. And then during the training time of diffusion model, an input image will be fed into the model, the UNet backbone, and then the conditions such as a semantic map, text, representations, or images will be incorporated by either concatenation or cross-attention into the UNet. The UNet architecture has been widely used in state-of-the-art large-scale text-to-image diffusion models, and these models include Imagen, Stable Diffusion, and Edify. Besides UNet architecture, vision transformer-based architecture has also emerged as a very promising architecture for diffusion models. So basically, the key idea is to treat the image as patches, image patches as tokens and employ landscape connections between shallow and deep layers. And in the last year, transformer-based architectures has achieved very strong performance on image generation tasks. And then here are some examples of the generated images from transformer-based diffusion models. So for instance, in this paper, Scalable Diffusion Models with Transformers, the authors are able to generate very realistic images using the transformer architecture. And in this paper, when transformer fits all distributions in multi-model diffusion at scale, is able to generate very high quality images using text guidance. And these are the samples from their model. And in this paper, Simple Diffusion, end-to-end diffusion for high resolution images, the authors are able to use transformer-based architecture to generate very high quality, high resolution images based on guided by text. So there are actually like lots of amazing works in the transformer architecture and UNet architecture space, but due to the time constraint, we're unable to cover all of the topics. And we strongly recommend the audience to check out the paper list on our GitHub repo. So next, we'll talk about image editing and customization methods with diffusion models. So in this section, we'll talk about image editing and customization using the following 3 different guidance. So first, we'll talk about how RGB pixels can be used to provide guidance to image editing of diffusion models. And then next, we'll talk about how we can use text guidance to guide the generation or editing of diffusion models. And then finally, we're going to talk about customization or personalization using reference images as guidance. So one application of generative model is actually guided image synthesis and editing. So where, let's say the user gives you a source image and they specify a general guide, such as using coarse color stroke, and we will often want the generative model to learn to fill in these details. There are actually 2 natural desiderata of guided image synthesis. So the first one is we want the generated images to appear realistic. And the second, or like with high fidelity. And then the second desiderata is that we want the generated image to look faithful to the input guide. In this case, this allows people with or without artistic expertise to produce photorealistic images from different levels of detail. Guided image synthesis and editing has been mainly dominated by GAN-based approach in the last few years. So the question here is that, how can we perform guided image synthesis and editing using diffusion models? So SDEs is a diffusion model-based approach that can be used for image editing and guided synthesis with RGB pixel guide. So given basically the idea is that given the user input guide, which for instance in this example is a stroke painting, we can first perturb the input with Gaussian noise, and then progressively denoise the image using a pre-trained diffusion model. this process, as we can see, will gradually project the input painting to the manifold of the images by denoising. And then note that here, we only need to use a pre-trained diffusion model. And then there's no, this approach doesn't require actual task-specific fine-tuning or retraining, because all you need to do is to, take this image, perturb it with a little bit Gaussian noise, and then denoise. So given an image, users can actually specify their preference by adding colored stroke to the image. And then in this example, SDE ADE will first perturb the input with Gaussian noise, and then gradually remove the noise, just as we mentioned previously. And within this procedure, this will generate a clean image that is both realistic and faithful to the user's preference. And the users can also demonstrate their creative ideas using strokes on an empty canvas and using exactly the same approach, and also only a pre-trained diffusion model checkpoint. SDE ADE can then generate a realistic images based on the user's painting, as shown on the left here. And this is actually the results. Besides application on diffusion models, SDE ADE is also compatible with latent diffusion models such as stable diffusion, where basically given this input, we can apply a sequence of denoising steps to the latent space, which gradually maps the input image to a high quality image of a specified style. So in this example, on the left, we show the input, and then on the right, we show the output, which corresponds to 2 different random seeds. Besides stroke-based image synthesis and editing, SDE ADE can also be applied to image compositing, where given an image, users can specify their preference by using pixel patches, which is shown here, copied from the other reference images. And then using exactly the same denoising approach and using only the pre-trained diffusion model, SDE ADE will first perturb the input with Gaussian noise, and then gradually denoise the noisy image to clean image using a pre-trained unconditional diffusion, using a pre-trained diffusion model. And using this approach, diffusion-based editing approach, is able to generate an image that is both realistic and faithful to the user's preference. However, one key limitation of diffusion-based image editing approaches is their slow inference speed, because to generate an image, diffusion-based approach usually requires passing the entire input into one deep neural network tens to hundreds of times, and this process is often very slow and very expensive. To deal with this issue, Li et al. Introduced sparse incremental generative engine, which is an engine that selectively performs computations in the additive regions from image applications. So basically, the key observation is that when users are performing image editing, they often edit only parts of the image. Like for instance, in this example, the user is only editing the sky, basically to add clouds to the sky. And there's only around 11.5% of the pixels that are being edited. And then basically we can design very smart algorithms so that we can only do computation on the regions that requires editing. And then in this case, it can drastically reduce the computational cost of diffusion-based image editing approach. And then using this approach, the authors actually show that the proposed approach can significantly reduce the computation while preserving the image quality. And then these are some more results from the proposed algorithm. And recall that in our previous session with Arash, we talked about DDIM, which is an inference approach for improving the sampling speed of diffusion models. So just to recap here, DDIM is actually a process that is deterministic. So basically, it will start from, let's say, a Gaussian noise sample in the latent space, and then it will deterministically map this Gaussian noise to an image in the image space. So since this procedure, this process, DDIM, is deterministic, we can also do the same thing, but in a reverse way. So basically, we can map any image in the image space deterministically to the latent space using the DDIM model. And then in this case, we're able to, deterministically pair an image in the image space with a noise in the latent space. And then this process is actually often called DDIM inversion. And then DDIM inversion is actually a very commonly seen approach used in image editing applications. So for instance, we can actually use DDIM inversion together with DDIM to perform image style transfer. So to do this, let's say we have a pre-trained diffusion model, and then we can, now we have an image of a tiger in the image space, but our goal is to, transfer this tiger image input to a photo of a cat, but which preserves similar style. So one thing we can do is that we just take the pre-trained DDIM model, and then we take this tiger image as an input, and then we condition our DDIM model on the class labeled tiger. And then we perform DDIM inversion of this tiger image condition on the prompt, the class tiger. And then this allows us to deterministically map this image of a tiger to a latent space of a conditional diffusion model. And then in order to generate a cat of a similar style, we basically take the diffusion model, but we condition it on the class label a cat. And then we can we take in this latent as input. We condition our diffusion DDIM model on the class label cat, and then we perform DDIM inference. Because DDIM inference is also deterministic, this will deterministically give you an output which tends to which often preserve the style of the input tiger image. And then a very good thing about this approach is that you don't really need to retrain your model because it's all like plugin and play. Basically, you can just take an off-the-shelf diffusion model, and then you just condition it on different prompt or different labels. You do DDIM inversion, and then you inference with DDIM condition on a different prompt or class. This allows you to do style transfer. And another nice thing about DDIM inversion is that because it also allows you to do multi-domain translation. Because all you need to do is to, let's say you start from this lion image in the middle, and then you just use DDIM inversion condition on the class label the lion, and then you to generate different animals, but which preserve the style, you just need to apply DDIM, the condition on different class labels during the inference time, the denoising step, and then it will gradually map this lion input to the output of different animals, different class, but all of them will preserve the style of the lion. And then another application of this approach is that you can also perform color transfer. So basically, let's say we have a reference image shown here. We also have a source image here. But let's say we want to modify the color of the source image to match the reference image. This approach also allows you to do that. So basically, you just need to learn this transform in the color space, and then apply this DDIM inversion on the color space. It will gradually it allows you to transfer the color of the source image to the reference image. So okay, now we're going to talk about diff-edit. So diff-edit is another approach for diffusion-based image editing. So basically, as we mentioned previously, in SDE edit, it often requires user to provide a mask, but like providing the mask can also be very expensive, and it's also very inconvenient. So in this paper, instead of requiring the users to provide the mask, diff-edit is able to actually automatically generate a mask highlighting the regions that needs to be edited based on users' input. So to achieve this, the authors proposed a three-step approach. So in the first step, diff-edit will actually add noise to the input image and denoise it based on the two different text inputs. So the first text input, will be conditioned on the query text, and the second one will be conditioned on the reference text. And we can actually derive the mask based on the difference on the two denoising results, because now we actually have like two outputs. The first one is conditioned on reference text, and the second one is conditioned on the query text. So intuitively, the difference in the result will actually tell you that which are most likely to be edited. And this actually can be used to generate the mask for image editing. And then in the second step, the authors propose to encode the input image with DVIM inversion. So this step will deterministically map an image to a noise in the noise space. And then in the third state, in the third step, Diff-Added will perform DVIM decoding, which is the DVIM inference starting from the encoded latent we got from step 2. And then this decoding process will also be conditioned on the text query, and it will also use the mask we derived in the first step, because not all of the regions needs to be modified. And then by combining step 1, step 2, and step 3 together, the authors are able to achieve very strong image editing results, but it doesn't require the users to provide any masks. Empirically, Diff-Added also, Diff-Added, as I mentioned previously, achieves very strong performance. And here are actually some more examples from Diff-Added. So in this example is actually on the imaging data set. And as we can see, Diff-Added is able to perform editing on the concepts while being realistic and faithful to the inputs. And besides these results, Diff-Added also achieves state-of-the-art editing performance on ImageNet. And in addition, it is also able to achieve very strong semantic image editing results on the COCO dataset, as well as text-based generated images. Imagic is an approach that allows for complex text conditioned image editing. So, for instance, let's first take a look at their results. Let's say we have this input image which is of a bird, and then Imagic can actually, if the users provide the text a bird spreading wings, Imagic can actually edit this image to make the bird spread its wing. Let's say we have an input image of a dog, but now if the users provide you with the text prompt, a sitting dog, it can actually make the dog sit. So for instance, there are more examples. So basically, let's say given this input image, the users can actually provide the text prompt so that Imagic will be able to modify this input image to align with the text prompt while preserving the original correct characteristics of the input image. So now let's dig deeper into the approach of Imagic. To do this, let's say given this real image and the target text prompt, the authors propose to encode the target text to first get an initial text embedding. And then after that, the authors then optimize the initial text embeddings to reconstruct the input image. And this would actually provide a fine-tuned text embedding that best helps the model reconstruct the original image. And this procedure is actually shown in the step A on the left-hand side. And then after we have obtained the optimized text embedding, in step B, Imagic will fine-tune the diffusion model to improve the fidelity of the input image while fixing, using the optimized text embedding learned from step A. And finally, in step C, the authors propose to interpolate between the original target text embedding and the optimized text embedding learned from step A to generate the final results. And then the diffusion model used in this process would be the fine-tuned diffusion model learned from step B. And here are some more results from Imagic. In the first row, we visualize the inputs of the model. So as we can see, these are trees, dogs, and a couple animals. And now the users can provide a couple text prompt, which will guide the input image to generate some new concept. And then as we can see, Imagic is able to successfully apply the desired edit while preserving the original image details as well. So for instance, if we take a closer look at this example, now the users would want to transform to add this input to like the tree with autumn leaves. And then by using Imagic, it is actually able to, you see that, like change the colors of the leaves, and like it's actually getting more like a tree in autumn. Okay, cool. So next, we're going to talk about another image editing approach based on text guidance, and the approach is called prompt-to-prompt. So prompt-to-prompt is actually a text-guided image editing approach based on diffusion models. It paves the way for various caption-based editing operations, including fine-tuning the level of the influence of an adjective word, making local modification to the image by replacing or adding a word, like shown here, or specifying a global modification. So these are the results. These are some results from prompt to prompt. So let's say we have this bunny door, and then like I would want to make this door more fluffy. So basically prompt to prompt can help you achieve that. So basically you can put more weights on fluffy, and eventually it's able to generate a bunny door which looks the same as the input image, but it's going to be more fluffy. And here in this example, let's say we have like a castle. We have an image of a castle next to a river. But now let's say we want to, you know, transfer it into the style of children's painting, children's drawing, and prompt to prompt can also achieve that. So basically, you just, you know, append this text to the original prompt, and then it can help you generate a children's painting, but of the same style as the input image. So to perform such text-guided editing, prompt-to-prompt proposes to control the attention maps of the edited images by injecting the attention maps of the original image along the diffusion process. So as we can see, this process is actually shown here. So this approach enables the users to monitor the synthesis process by editing the textual prompt only. This allows for various caption-based editing applications, such as localized editing by replacing a word, global editing by adding a specification, or even controlling the extent to which a word is reflected in the image. So here are some more results from prompt to prompt. As we can see, prompt to prompt is able to faithfully perform editing to the target image using text guidance. So for instance, in this example, if we reduce the weight of the word birthday, prompt to prompt is able to gradually, you know, like put more weight to birthday. And as we can see, the cake, the birthday cake eventually transform into a cake, but without candles on it. And in this example, by varying the weights of the term blossom, as we can see, using prompt to prompt, the blossom on the branches gradually start to vanish. And in this third example, let's say if we want to increase the weights of the word snowy, and prompt to prompt will gradually, you can see that like it will gradually add more snow to the input image as shown here. Instruct pix to pix is another approach that allows for image editing based on instructions. So specifically, given an image and an instruction for how to edit that image, the proposed model will perform the appropriate edit. And a very good thing about Instruct pix to pix is that it does not require full description for the input or output image. And moreover, Instruct pix to pix also edits image only in the forward pass, and it doesn't require per example inversion or fine tuning. So these are actually some. This is actually the figure from the Instruct pix to pix paper, and as we can see, so let's say like we have this let's say we have this input image, and then by providing this instruction, swap some flowers with roses, the Instruct pix to pix is able to transform this input image into a painting, but swap this sunflower with rose. And this is also a very cool example So let's say we have this image here, and then now let's say we want to add fireworks to the sky. Instruct Pix2Pix can also do that. And as we can see, the results are actually very impressive. They're of very high fidelity, but also preserve the concept of the input image. So specifically, Instruct Pix2Pix consists of 2 parts. And then in the first part, the authors propose to generate an image editing dataset and then train a diffusion model on that dataset. So to generate this dataset, the authors first use a fine-tuned GPT-3 to generate instructions and edited captions. And then the authors use stable diffusion together with prompt-to-prompt to generate pairs of images from the pairs of captions. And using this procedure, the authors are able to create a large dataset of training examples. And then once the dataset is ready, in the second part, the authors actually train the Instruct Pix2Pix diffusion model based on this generated data and added the images based on the instructions. And at inference time, the model is able to generalize very well, and it can generalize to add the real images and based on unseen human instructions. And this is actually the result from Instruct Pix2Pix. And as we can see, the results are very impressive. Another very interesting problem in real-world application is about personalization and customization, where the users would like to generate created images based on the character from some reference image. So for instance, in this example, let's say the users have a couple, like 3 to 4 images of a corgi as shown on the left. And then the question is, how can we learn a model that is able to generate creative images of the same corgi, but in different settings? Like for instance, how can we generate the same corgi, but is swimming, let's say in the swimming pool? So, so in this section, we're going to talk about personalization methods. So in general, such customization is actually a very challenging task. So let's first take a look at this example. So let's say like we have a particular style of a clock, which is shown on the left as the reference images. It's actually very challenging to generate the same clock in different contexts with a state-of-the-art text-to-image model while maintaining the high fidelity of the key visual features. So for instance, if you take off-the-shelf state-of-the-art models without actual training, DALL-E 2 and Imagen both struggle to generate images that preserve the high fidelity. So for instance, you can see that the pattern on the clock actually changed if you just directly take off-the-shelf DALL-E 2. And even for Imagen, you can still see that the pattern on the clock has changed if you just directly take the model. So to deal with this issue, the authors of Dream Booth proposed to fine-tune the model using the input images of the subject, which is usually, in this example, it's going to be input images of the same dog, 3 to 5 images of the same dog. So to encode the concept of the input, the authors proposed to pair the input image with a text prompt containing a unique identifier and the name of the class of the subject. So for instance, the unique identifier will be this token, will be this part here, and then the class would be the dog in this example. To actually generate diverse instances belonging to the subject's class, the authors also propose to apply a class-specific prior preservation loss as shown here. And this actually leverages the semantic prior that the model has on the class, which is a dog in this example. And this actually allows the model to generate more diverse outputs and prevents overfitting. Using the proposed Dream Booth method, the authors are able to generate different images of the same subject in different environments. And for instance, in this example, the reference image are actually the backpack shown on the left. And then we can see that using Dream Booth, we're able to generate the same backpack, but in different settings. And then here's another example of a teapot. The reference image is shown here on the left. And by using Dream Booth, we are able to generate different images of the same teapot, but in different settings. And as we can tell from these results, Dream Booth is able to generate like very high fidelity images based on the reference image. And also the results is very diverse. And moreover, it also allows for the realistic interactions between the scene and the subject if we pay close attention to these results. Dream Booth also have lots of very diverse applications. So for instance, it can also be applied to text-guided view synthesis, and it can also be applied to art renditions as shown here. And there are actually like many other applications of Dream Booth. Because of the time constraint, we're not able to cover all of the exciting applications. So we strongly recommend the audience to check out the paper if they're interested in it. Okay, cool. So next, we're going to talk about textual inversion. So textual inversion is another approach that allows for customization, and it only uses like around like 3 to 5 images. And basically using these only 3 to 5 images of a user-provided concept like an object or a style, textual inversion learns to represent the concept through new words in the embedding space of a frozen text-to-image model. And these words can be composed into natural language sentences, and it will guide personalized creation in a very intuitive way. And in this paper, the authors also find that a single word embedding is sufficient for capturing unique and varied concepts. So these are some results from textual inversion. So for instance, in this example, the users will provide, let's say, 4 images of this concept. And then by using textual inversion, the model is actually able to generate the same concept, but in different style or in different context. And as we can see, textual inversion is able to achieve very strong performance on this task. For instance, we can see that like if we care about let's say the concept, like textual inversion is able to generate the same concept as the input image. And even for the pose, let's say like we care about the pose of the input image, and textual inversion can also achieve that. So you can see that it can actually transfer the same pose but to a different character as shown here. Here is an outline of the approach of textual embedding. So basically, the process contains, like in this process, there's going to be a string containing a placeholder word, and it's going to be first converted into token. And then the tokens will be converted to continuous vector representations that is also known as the embeddings shown here. And finally, the embedding vectors will be transformed into a single conditioning code which guides the generative model. And the embedding vector, which denotes V star, is actually associated with the pseudo word like S star, and then it's going to be optimized using the reconstruction objective. Here are some more results of textual inversion. As we can see, textual inversion is able to capture the concept and generalize to new concept using the pseudo word derived from the input samples. So for instance, here, the pseudo word is actually S star. And then basically by using textual inversion, you're able to transfer this style to new concepts. And as we can see, the results are very, very impressive. Moreover, the textual embedding space can also represent more abstract concepts, including styles. And this allows the users to discover words which can be used for style-guided generation. So for instance, here, these are the input samples, and it's actually the style image. And then by using textual inversion, the users are able to generate paintings of different contexts, different concept, but based on the style. And as we can see, the output results actually really maps the style of the input samples very well. In general, a challenge of customization or fine-tuning diffusion model is that this process is often very slow and computationally expensive. And also storing this fine-tuned model is often very expensive because diffusion model or these large-scale text-to-image model are often very large and they have so many parameters. So low-rank adaptation attempts to solve this issue by fine-tuning the residual of the model instead of the entire model. And it proposes to approximate the residual with low-rank matrix approximation. And because this residual is actually approximated by low-rank matrices, low-rank adaptation is able to drastically improve the efficiency of the fine-tuning process. And also it's more memory efficient. Here are some results of stable diffusion fine-tuned with low-rank adaptation. And this fine-tuning is only processed on 9 images. And we visualize the results after each 500 iterations. As we can see, the fine-tuning with low-rank adaptations is able to converge very, very quickly. So these are the results. Another interesting question about fine-tuning is, like, should we fine-tune the weights of the entire model or should we only fine-tune part of the model? So in general, tuning the entire model, as we mentioned previously, is often very computationally expensive if the model is gigantic, and it also requires larger storage. And moreover, if let's say the input concept is only 3 to 5 images, if you fine-tune the entire model, if you train a model for too long, it can easily cause overfitting. To provide more insights into which parameters we should perform fine-tuning on, we can actually analyze the importance of different parameters of the models. So usually the parameters of diffusion models comes from 3 different types of layers. The first layer is the cross-attention layer, which is the layer trying to combine the feature of the text and image. And the second type of layer is the self-attention layer, which is performed within the image itself. And the third type of layer is the rest of the parameters, including the convolutional blocks and normalization layers in diffusion model UNet. Now we can plot the change in weights of these 3 different types of parameters between the pre-trained model and the fine-tuned model. So as we can see here, after plotting the change in the weights, the authors observed that the change in the relative change in cross-attention layer is actually the most significant compared to the other different types of layers. And this actually kind of implies that cross-attention is more likely to play a more important role in the fine-tuning process compared to the other parameters. So inspired by this observation, the authors proposed to restrict the updates to only the WK and WV parameters of the diffusion model during the fine-tuning process. So basically, we only train the authors proposed to only train the WK and WV parameters of the diffusion models during the fine-tuning process, but keep all of the other parameters frozen. So to further prevent overfitting, the authors also proposed to add regularization images during training. And then the regularization images can actually be retrieved from large-scale text-to-image models such as Lion. Basically, you can do this by computing the textual caption similarity, and you can just choose the images based on how similar the caption is with the captions in the training data, and then retrieve the images accordingly. And for instance, in this example, the target image is about the moon gate. And if you do the retrieval from, let's say, Lion data set based on the textual similarity score, and then the added regularization images are actually the images shown on the right. And as we can see, they're like textually similar to the target image on the left, and the authors show that adding these regularization image is actually super important, useful to prevent overfitting. And in the case of personalized concept, we also need to decide how to describe that specific concept of that category. So for instance, let's say if I want to generate my friend's pet dog through Stable Diffusion model, and fine-tuning just the text caption, a photo of the dog will change all dogs to my friend's pet dog, which is not ideal. So to prevent that from happening, the authors propose to add the modifier token V star in front of the category dog, and then V star in this case will be a new token in the text embedding space. And the authors propose to train the V star as well, along with the key value projection matrices during fine-tuning. So basically, these are the parameters that will be trained during the fine-tuning process, while the other parameters of the model will be frozen. So putting things together, the proposed approach is able to generate high-quality images based on the input concept as shown on the left. So for instance, given these 4 images on the left of my friend's pet dog, the proposed approach is able to generalize to a new concept. For instance, it can actually generate the same dog, but wearing headphones. But what if we want to compose 2 new concepts together? Let's say we want to generate my friend's pet dog in front of a structure like Moongate in a garden. And then we provide these 2 concepts, Moongate and the dog. So to deal with this, the authors show that you can actually fine-tune the model on the 2 concepts based on the 2 datasets together. And then in this example, it's going to be the dataset of dog images and the dataset of Moongate images. And you will also train the model with the corresponding regularization images. With this approach, the authors show that the proposed method can achieve very strong performance on 2 concept generation tasks. For instance, in this example, the 2 concepts would be the cat and the wooden pot. And then by joint training, the model is able to generate the concept with both the cat and the wooden pot in it, as shown on the right. Here's another example where the 2 concepts are sofa and the cat. As we can see, the proposed method is able to capture the 2 concepts very well in the generated images. So for instance, there's actually like interaction between the 2 concepts, but the model is actually able to capture it very well. So next, we're going to talk about another approach for image personalization, and it's called perfusion. So perfusion is another text-to-image personalization method that addresses the challenges of personalization using dynamic rank 1 updates. So perfusion avoids overfitting by introducing a new mechanism that logs the new concepts cross-attention keys to their subordinate category. And additionally, the authors develop a gated rank 1 approach that enables one to control the influence of a learned concept during inference time. And it also allows the model to combine multiple different concepts. And the authors show that perfusion is able to perform very strong on the baseline shown here. And it's also able to achieve a very strong results, even when combining different concepts together. So these are the results of perfusion. So in the middle, so basically the training examples is shown on the left. And in the middle, these are results of diffusion but condition customized on 1 single concept. And then on the right-hand side, on the right panel, these are the results of perfusion, but trained on combined concepts. And as we can see, perfusion is able to model the interactions between different concepts very well. Another approach to perform controllable image generation is to introduce an actual adapter. So in this paper, the authors propose a simple and light-weighted model or adapter to provide actual guidance to a pre-trained text-to-image diffusion model. So the architecture of the adapter is shown on the right. So basically, it is composed of 4 feature extraction blocks and 3 downsample blocks to change the feature resolution. And the proposed adapter can be directly applied to off-the-shelf text-to-image model. It's very simple, it's very lightweighted, and it's very easy to use. the adapter can also be trained on different forms of input, including style, sketch, canny, or depth map. The authors show that different adapters can actually be combined very easily to serve as a new guidance for content generation. And with the proposed adapter, one can generate very creative and controllable results based on different forms of input. And these are the results from the T2I adapter. And as we can see, T2I adapter is able to achieve very impressive results. So for instance, condition on these edges, it can generate a realistic image. And then condition on these two different concepts, it can generate an image that follows the two concepts very well. Control net, next we're going to talk about control net. So control net is a neural network architecture that can be used to control diffusion models by adding actual conditions. So the control net learns task-specific conditions in an end-to-end way. So specifically, control net can be applied to an arbitrary neural network blocks. So here, let's say we have this neural network block shown here, and then the input is X and the output is Y. So let's say now we will want to condition on different concepts, and then we can introduce control net block as shown here. So basically, it's gonna take this condition context as an input to this branch, and then it will be combined with the input X, and then the X will be fed into this new branch control net. And eventually, once you got the results, the output of control net will be added to the output of Y. So here, the addition notion here refers to the feature addition, and the C here is the actual condition we would like to use. And then the zero convolution here is an one-by-one convolution layer with both weights and bias initialized as 0. So as an example, control net can be directly applied to stable diffusion as shown on the right. So here, the gray blocks are the structure of the original stable diffusion, and then the blue blocks are blocks from control net. So to train the control net version of stable diffusion model, we can use the following objective. So basically, the T here is actually the time step which will be used in the noise scheduling, and the CT is actually the text prompt embedding, and then the CF is actually the task-specific conditions from the control net, and then we'll just be training our diffusion model using the same objective function, but it will be conditioned also on the CF, which is the task-specific conditions from control net. The input content of control net can be very diverse. For instance, it can be the line input, and then these are the results of control net when conditioned on the line inputs. And as we can see, the results are actually very faithful and realistic, and it strictly follows the input lines shown on the left. Control net can also be used to control stable diffusion with HED boundary map. So these are the boundary map shown shown on the left. And then here we visualize the results. And as we can see, using control net, the model is able to generate very high quality results, but very faithful to the input boundary map. Control net can also be used to be conditioned on open poles as the input. So basically, these are the input, and by using control net, you are able to generate very high quality outputs, but which also faithfully follows the input of the open poles as shown on the left. So Glidgen is actually another model architecture which can be used for text to image generation. So basically, the way Glidgen works is that it will introduce new parameters by adding a gated self-attention layers between the self-attention and the cross-attention layer within the encoder. And the details of the gated attention, self-attention are depicted in the left part of the following figure. And the difference, and then on the right, we actually visualize control net. And as we can see, the core difference between collision and control net is that collision process concatenation of condition and visual features with the transformer layers, whereas control net processes the sum of condition and visual feature, which is more suitable for spatially aligned conditions. And empirically, by using collision, the model is able to generate very high quality results given different types of input. So for instance, collision also can be applied, can be directly applied to very diverse form of input. For instance, box plus text plus image, and many more. And then these are the results from collision. And as we can see, like these results are very impressive. And for instance, let's say like we use this box plus text input as shown here, and the model can actually generate the image which follows the right composition, but also follows the content of the prompt. And then in this example, like we can also use a different input, and as we can see, the results are like very, very impressive. So finally, we're going to talk about different other applications of diffusion models besides architecture or customization or image editing. So first, we're going to talk about how diffusion models can be applied to image classification and different downstream tasks. So although in general, although diffusion models are commonly used for data generation purposes, a recent work actually shows that the density estimates from large-scale text-to-image diffusion models like Stable Diffusion can actually be leveraged to perform zero-shot classification without any additional training. So specifically, given an input image and a set of possible conditioning inputs, like let's say the text prompt in this example, the authors propose to use a diffusion model to choose the one that best fits the image. So the authors show that the proposed diffusion model-based method approaches can actually matches the performance of state-of-the-art discriminated classifier. This is actually very promising because it shows that the feature learned from the diffusion model can actually be applied to downstream tasks such as image classification tasks. So diffusion model is also shown to be able to improve the robustness of the classifier. In a very recent work, the authors of improving robustness using generated data explore how generative models like diffusion models can be leveraged to artificially increase the size of the training set, and how syntactic data can be used to improve adversarial robustness. And to achieve this, the authors propose to first train a generative model and a non-robust classifier, which are used to provide pseudo-labels to the generated data. And then the authors propose to use both the generated data and the original training data to train a robust classifiers. Empirically, the authors show that such approach is able to drastically improve the robustness of a classifier. In another paper, Wang et al. Also show that generated data from diffusion models can be used to improve adversarial training, and specifically, the model using generated data from diffusion models can be used to achieve state-of-the-art performance on CVPR 10 and CVPR 100 datasets. Because of the time constraint, we're unable to go very deep into these amazing papers. So like I would strongly recommend the audience to check out the papers if you're interested in the topics. So finally, I would like to thank everyone for contributing to our tutorial. And I would also like to thank Junyan for sharing his slides on customization. And here is the list of reference covered in this tutorial. And finally, I would strongly recommend everyone to check out these amazing papers and also the papers on our tutorial website. And because of the time constraint, we're unable to cover all of the details, but so we strongly recommend people to check it out if you're interested in the papers. So, okay, so that's the end of my tutorial. So I'm happy to take questions if anyone has questions. Yeah, so I think Anna, I saw you raising hand, but okay, yeah.
Thank you for the talk. So I had a question about the image customization aspect. So I think most of the examples you showed were concerned with either style or texture or things of that sort. But what about like the geometric editing part? For example, if you want to move an object or things of that sort.
Yeah, I think that's a very good question. So basically, I would say like if you want to do customization on that part, like you can also provide, let's say, a few guidance with respect to that aspect. And then I would say like you probably also need to deal with some domain specific knowledge, but I would say it's also very likely to work if you provide the guidance properly. Yeah. So I think it's going to be more about like the input preference you input into the model.
Thank you.
Yeah.
If you have any question in the room, you can walk to that microphone, ask Chenling there. Okay. If not, we are right at the top of the hour. So thanks, Chenling, again. So
you.
we can take a 15-minute break and come back again at 11:30. Thanks. Thanks, Chenling.
Thank you.
All right, I guess let's resume the session for the third part. Okay, yeah. Hi, everyone. I'm Jiaming. I'm a research scientist at NVIDIA. And this section will be talking about applications on other domains than images. And specifically, we will first, this will consist of 4 sections. So first, we will talk about some applications on plug and play style inverse problems. And then we will talk about 3D. And then on video, and lastly, we will cover some miscellaneous topics. So this section will contain a lot of papers. So again, apologies for if we weren't able to cover like the papers you like, but we try to keep the ones that we think are the most relevant to the community. And for inverse problems, we are let's go into this section. So basically, the idea of using diffusion models as a plug and play priors can be seen as this. So suppose that we are going to do this task, which is trying to denoise and super resolve this particular image. And it's basically this ill-defined problem because many potential high resolution images might be downsampled to this one. But there are specific priors in the data set that we want to leverage. So for example, let's say our diffusion prior just contains 2 images, and we can obtain the likelihood of generating this this noisy
image based on like particular like samples in this prior. And we can see like one of the images is probably more likely to generate the, like low resolution image than the other. And therefore we can reach a posterior by doing something similar to a Bayes rule. What's really nice about this plug and play approach is that the task is kind of plug and play. So now we consider a different task, which is to just recover the mask region of an image. And this image is an entirely different image. It's an entirely different task, but we use the same diffusion prior. And basically, this means that we can just change the likelihood, which before was considering the forward function of super resolution, but now we consider the one for in painting. And we, by applying like, Bayesian posterior sampling again, we can reach a different posterior. And in this setting, we want to use the same diffusion model for different problems. I know there's a lot of research on like using like trained diffusion model for like specific problem only. And I want to make a distinction from these line of works that were covered somehow, somewhat in like Chen-Lin's part. So there are two major paradigms to solving these with diffusion models. So the first part is what I would call replacement-based methods. So the idea is that the model makes a rough prediction and we have some certain observations. So for example, here, this is a mask image where I want to inpaint the middle bit. The replacement-based method basically tries to replace the model prediction with the new prediction. And we are going to just use this new prediction as if it is our model prediction and use that in the diffusion process. And another type of method, which is called reconstruction-based methods, which instead of trying to replace the observations directly, it tries to optimize a loss function overall of the observations and then backpropagate this information through the diffusion model. So by changing that, we try to approximate classifier-free guidance, but the difference between this and classifier-free guidance or classifier guidance is that we do not require additional training. So one very simple example for replacement-based methods is as follows. So suppose that our diffusion model currently gives us a denoise result, and this denoise result for like illustration purposes is pretty far from what we are currently observing. So there's like a very different colored block on the right. And we observe Y, which is a mask region. So by doing this linear combination, we basically overwrite our existing model prediction with our observations. And therefore, we will get this updated denoise result. And with this, we can basically combine the current input xt, the updated denoise result, and some Gaussian noise, and combine it to get the next step. And for example, this combination can be some kind of a sampler such as DDIM. The reconstruction-based methods worked differently in a way. So essentially, as we said earlier, this tries to approximate classifier guidance. So recall that the classifier guidance can be treated as we want to estimate the conditional score of P of xt given Y with the sum of the score of the prior diffusion model that does not depend on Y with the part that is conditional on Y given xt. So before in classifier guidance, this is done by training on pairs of X and Ys. And here we want to do this without training. And specifically, this relationship between X0, Xt, which is a noise data, and Y is a Markov chain. So basically, you can get Y from X0, for example, what is the master version of it, and get Xt from X0 by adding noise to this process. And the way you approximate this classifier guidance term is to first realize that because of this is a Markov chain, you can do an expectation over the possible like X0 predictions. So this is just a simple application of the marginalization in Markov chain. And the next step is an approximation. So instead of directly taking the expectation outside of the probability, we move the expectation inside. So basically, we instead consider using the expectation of X0 given Xt as the conditioning for Y. So here, this expectation is the denoiser output. So essentially what we are going to do is that we are going to construct a probability or loss function based on the denoise result that is given by the diffusion model. So for example, if you assume that the loss is Gaussian, then it's basically just trying to compute the L2 distance between the measurement, which is provided as the information, and the generated data. So in this case, for example, in this paper called Diffusion Posterior Sampling in actually 2023, the idea is that we generate the X0 prediction based on a noisy image. And then we are going to use this matrix A to project that to only retain the non-masked region. And then we are going to compute a loss function on over the real non-masked region. And by minimizing this loss, we can go closer to the correct image. And there are multiple different methods on solving these inverse problems. And due to the interest of time, I can't go to details of too many of them, but there's a long history of reconstruction-based methods that started from simple linear problems and which were then extended to more linear problems and then noisy linear problems. And then people introduced better initializations. And finally, there are faster solutions for all the noisy linear problems, as well as some nonlinear ones such as JPEG. Similarly, there's a very long list of literature on replacement-based methods as well. These were initially used for super resolution and then were extended to linear and some nonlinear problems. And finally, people can combine replacement and reconstruction methods for certain linear problems. There are other solutions that doesn't strictly fall into the two categories, such as CSGM, which uses posterior sampling with longevity dynamics, a red diff, which basically combines the very famous regularizing by denoising method and variational inference, as well as posterior sampling, which uses a real MVP to another generative model to help you approximate the posterior samples from diffusion models for faster inference. So next, we are going to talk about 3D, and this is a very huge topic, so it will contain multiple sections. So first, we're going to talk about diffusion on the various 3D representations. Then we will talk about 2D diffusion models for 3D generation. Next, we will talk about diffusion models for view synthesis. So these are not strictly 3D. Lastly, we will talk about 3D reconstruction and 3D editing applications. So for diffusion models for point clouds. So one of the easiest kind of representation for a 3D object is just a point cloud. So a point cloud is specifically just a set of points with location information, for instance, or other kind of information such as color. So the procedure of generating a point cloud with diffusion model is actually quite simple. So let's say we start with we assume first of all, let's say all the information is just a location. So we can just randomly initialize our point cloud. Here is P of capital XT with a Gaussian distribution over all the points. So now all the points were initially randomly distributed as a Gaussian distribution. And then we run the diffusion model process over the point cloud and iterate until finally we will reach good enough sample. And in this case, it's the point cloud looks like a chair. However, the architecture of the point cloud is slightly different than what you would expect in the image. So one of the most popular architectures is what is called point voxel CNN. So what point voxel CNN does is that it has two branches. So the first branch is basically a multi-layer perceptron over each point. So each point is going to have a multi-layer perceptron mapping to each point. This is similar to transformer, except that we don't have there's no self-attention layers in between them. Another branch is the voxel-based approach. So the idea here is that it wants to use the location of the voxel grid of the points, and they aggregate them into different voxels. So these voxels have lower resolution than the number of points, hopefully. And then after the voxelization, people can use traditional convolutional neural networks like 3D ConvNets to do this feature mapping, so that these features are location aware. And then you can devoxelize and then fuse this information to the MLP. So this is kind of the high level idea of the point voxel CNN architecture. And back in 2021, it has already been used for point clouds, including several tasks such as generation of ShapeNet objects, as well as certain type of completion. So in this completion, it's basically trying to complete with a depth map. So basically, given the depth map, what would be the point cloud of an object that satisfies this depth map? And the idea is that you first get the points from the depth map and then do kind of in-painting techniques on the point cloud model. And of course, with every kind of original data space diffusion model, there's like latent space diffusion models. So Lion is a method that uses this latent like diffusion model for point clouds, and specifically they have this point voxel CNN architecture that encodes into shape and latent shape and then the latent points, and these are then modeled via a denoising diffusion model and then decoded back into the like actual point clouds. So this is like a latent diffusion model variant of point clouds. And of course, recently OpenAI released a paper called PointE, and it's basically also works on point cloud, but slightly different from existing approaches. So in their cases, they want to do text to point cloud generation. So basically, given an input text prompt, they want to generate a point cloud. And the idea that is done here is that, first of all, they input a text prompt, and then they use a fine-tuned glide model, which is just a fine-tuned text-to-image diffusion model, and they will generate a synthetic view. So basically, this is a synthetic view of a corgi, and this image model is fine-tuned on the 3D dataset. And then based on this synthetic view, there is a point cloud diffusion model that tries to lift the image into a 3D point cloud. So the architecture specifically is actually just a transformer where the clip image features are inputted as these tokens of conditioning input of the transformer, and then the point cloud features are also kind of input as the input of the transformer. The output, though, is only the point clouds. So the clip is only access conditioning. So next, we are going to talk about other representations. So for example, another very popular representation for shapes is called sign distance function. So a SDF or sign distance function is basically a function representation of a surface. So for each location X, the SDF of X is basically the absolute value of that is the smallest distance to this point onto the surface. So usually speaking, you can define this function that's just based on that. And in this example, we show different points at the crosses, and then you can draw different circles to determine like how far, like what is the smallest distance to this point to the surface. And usually speaking, for points outside of the surface, the SDF is positive. For points inside the surface, the SDF is negative. One problem with this type of representation is that because we try to we can model this function just by having this grid of SDF values. And in this case, the memory will grow cubically with the resolution. So in images, the resolution scales like in squared, but here it grows cubically. And the problem with that is it doesn't really support very high resolution generation. However, you can actually show that because the SDF generally has structure, you can use some techniques to first compress the SDF and then do generation. So one way to do this is to use wavelets. And in this case, the authors show that using certain wavelet is better than others. And I think the certain wavelet is closely related to the JPEG 2000. So the idea is basically that first, this SDF was processed by the wavelets to separate into coarse coefficients, which are low resolution, but describe the general shape, and then detailed ones that are like contains like more high frequency details. So the diffusion models were acted on the coarse coefficients. And then given the coarse coefficients, there's another detailed predictor model that tries to predict the detailed information. So by combining these two, you can get a diffusion model for SDS. Again, as for any method based on the original data space, there are methods that are based for a latent space where you can actually just encode the SDF into a latent space and then try to do diffusion models on this latent space. And in addition, you can actually add these conditional information via cross-attention. And this is a common technique used in diffusion model already. For other 3D representations, perhaps another very popular one is neural radiance fields or NURFs. So this is a different representation of a 3D object. So the high-level idea of a neural radiance field is that it tries to represent things in this voxel space. So basically, each point of the world contains the location information, so x, y, z, which are the world coordinates. And you can think of this you're trying to represent points in this 3D voxel world. However, in the world, different like surfaces might have like different reflection effects. So if you're looking at the mirror, then what you see is actually depends on like your viewing direction of the mirror. So in addition, the neural radiance fields also considers the viewing direction as the input. So basically, now you can determine sort of the color or the other like visible coefficients based on 5 parameters. 3 are the world location and 2 are the viewing directions. So the idea is to basically use the like multi-layer perceptron or a small neural network that converts this 5-dimensional vector into a 4-dimensional like RGB colors and as well as this sigma, which basically is the density. So basically, it shows how transparent this point is. And basically, after representing this, 3D world with a compact representation of the MLP, NERF basically acts by doing this like volume rendering technique, which we won't go into the details, but it's important to know that it is fully differentiable. So given a like rendered image, you can actually do propagation from the image to the underlying parameters, in this case, it's the MLP. And again, people have been, there's a lot of work on this NERF field as well, and people have considered many different types of representations. So this is a picture from the EGCD paper. So you can consider the original NERF technique, which just fully implicit, which is just use the MLP for everything. Or you could consider something like that's more closer to voxels, which is better in terms of like speed, but has like poor compression abilities, or something just in between. So you can find a factorized triplane representation to the voxels, and then maybe have a very small MLP to obtain the density and color results. Again, we won't go into the exact details of these methods, but diffusion models also have been used on these different 3D representations. For example, triplane diffusion just acts on the triplane representation. And a benefit of this is that the triplanes these representations can be easily combined with 2D units. And the second one is regularized ReLU fields. And another one from OpenAI again is called Shapey, which directly acts on the implicit MLP of NERFs. In all these cases, it's very important to find a good representation because in NERFs, typically the same like different MLPs can represent the same underlying NERF, but this might not be easy to learn by like a diffusion model if you consider a data set of NERFs. So finding a good representation is actually key to getting it work, and I think it's still an active area of research. So next, we are going to talk about another route, which is to use 2D diffusion models for 3D generation. So just now, we discussed diffusion models directly learn on 3D data. These have various advantages of being like able to sample relatively fast. However, the problem is that there are a lot fewer 3D data than 2D. So if you think about the Lion dataset, it contains like 5 billion images, whereas like big 3D datasets like Objectverse, they only contains about 1 million images. So people have been thinking whether we can use the rich information from the 2D diffusion models and use that as some kind of a prior or supervision to give us 3D objects. And it was actually quite successful. So this is the Dream Fusion paper where it all started. This was the iClear 2023 paper that got the Outstanding Paper Award. And you can see that it's able to generate a lot of diverse 3D objects that wouldn't be able to exist in the world, such as aliens playing chess or a wizard raccoon. So the specific setup is at this. So let's suppose that we have a text-to-image diffusion model. And the goal here is to optimize the NERF parameter such that in each angle, this 3D object looks good according to our 2D diffusion model. So if we somehow come up with this object and the 2D diffusion model thinks, okay, this looks good from every angle, then we would think that we have obtained a reasonable 3D object. However, the sampling approach is actually quite different because unlike the ancestral sampling approach that we've been introducing, such as DDPM or DDIM, the underlying parameters is not the 2D image space, but in the nerve space. And for example, these can be the weights of the MLP. So instead, this is considered an optimization problem where you try to optimize the nerve parameters to satisfy some objective function. And this particular approach is called score distillation sampling. And the idea is that we can get an image from and use the diffusion model to come up with a loss function. Then this loss function can backpropagate to the image, and this image can be further used to backpropagate information to update the nerve. So specifically, what is the objective function? So for now, let's consider the diffusion model objective for training a sample. So basically, in this case, it's just a denoising autoencoder objective averaged over different time steps. So we add noise to this sample, and then we denoise it, and this is the objective function. So if you directly try to compute the gradient of this, whereas you are trying to maximize the likelihood or minimize this diffusion loss, it will actually give you 3 terms. You can just easily derive this by a chain rule of calculus. So the first term is the residual of noise. So basically, what would your noise epsilon prediction or of the diffusion model, the difference between that and the epsilon, the Gaussian noise that you sample. The second term is this unit Jacobian. So basically, you take the Jacobian of the diffusion model's output over the input. And the third one is the generator Jacobian, which basically tries to differentiate from the input image to the underlying nerve parameters. The unit Jacobian is a problem because this means that basically we need to backpropagate through the diffusion model, and is not only slow, but also very costly in terms of memory. So it's not exactly a very desirable solution. However, in the Dream Fusion paper, the authors point out that it turns out that you can actually remove the unit Jacobian, and therefore you come up with a much cheaper objective function instead, without ever having to do backpropagation through the diffusion model. You still need to do backpropagation through the nerve, but it's much cheaper. So how do the authors come to this? So they consider this KL divergence term to minimize. Given, for example, let's consider a particular time step t, which tries to compare the KL divergence between this QZT of t and PZ of t. So here, QZT, a given G theta, is basically the rendering of the nerve and with added noise. So, and then P theta is just the noisy distribution of the real image. So basically this compares the KL divergence between the noisy real image distribution and the generated image distribution. And of course, these are conditioned on the text Y. And we can derive the KL divergence and the gradient as follows, and it contains 2 terms. So here, B is basically just, you can approximate it with the diffusion model. So you can basically obtain this by the chain rule, which basically is the diffusion model combined with the Jacobian of the nerve. And the first term, A, is the gradient of the entropy of the forward process. And recall that our forward process is just a Gaussian added noise. So in this case, taking the derivative of that, it just has a fixed variance, and that would be 0. However, this kind of objective function is quite noisy because each time you sample a random epsilon, and this random denoise result epsilon will also give you a noisy result. Alternatively, we could consider this approach to do variance reduction, and this is similar in spirit to reinforcement learning. So the idea is that you would add a component that has a 0 mean, but it has a certain act in the opposite direction of what your original objective has. So by adding this 0 mean component, you have an unbiased objective, but you reduce the variance. So in this case, we have the original A term has the mean of 0, and B term has a non-zero non-zero mean, which is tied to the epsilon prediction of your denoiser. So the idea is essentially just let's first add and minus epsilon inside each of these terms. And then we realize that this epsilon is just a Gaussian noise. So it doesn't really depend on any other of the hyperparameters like the nerf parameters. It doesn't depend on the image. It also doesn't depend on the time. So the mean of the Gaussian noise epsilon is just 0. So we can throw away one of the epsilons, and then we are left with this final term, which just computes the difference between the epsilon prediction of from the diffusion model and the epsilon noise that we add in this process. So again, this has the same mean, but with reduced variance because we typically train the denoiser to the epsilon model of the denoiser to predict the noise. And this is the entire pipeline. So again, it can be used to optimize the 3D representation like NERF, specifically from the NERF or any other kind of 3D representation, you can render an image over the camera pose. And in this case, after you get the rendering of the image, you add noise to this, you add noise to the image and then use the diffusion model to get an epsilon prediction. And basically you try to guide the nerve towards the right direction by comparing the difference between the epsilon prediction and the actual like sample noise. So SDS has been like really popular in the past like nearly a year. And there has been a lot of extensions and similar applications based on that. And one of them is in Magic 3D. So concretely, it does more engineering improvements on top of the original SDS. So it achieves like 2x the speed and also achieves results at higher resolution. So first, they replaced original NERF, which was quite slow, with a better like neural rendering architecture called Instant NGP. This was used over a small, like low resolution diffusion model for generating the coarse representations. And then conditional on this coarse representations, they then optimize a finer mesh model using a differentiable renderer over the like latent space diffusion model, such as Stable Diffusion, to get higher resolution 3D objects. A different alternative formulation to the score SDS is called score Jacobian chaining. So basically, this is a different formulation motivated from approximating the noisy score function of the 3D model. So basically, the idea is that you can approximate the score of the 3D as the expectation of the score of the 3D object, but over the 2D renderings. So basically, in this case, you want to get the 2D score of the noisy distribution, but over clean images, and then you again combine that with the Jacobian of the rendering process. So in principle, we can just use the diffusion model to get the noisy 2D score, but this is over clean images. So there's a problem that in practice, the diffusion model suffers from like out of distribution issues. And if you have a diffusion model that tries to predict score on noisy images, then the score over non-noisy images are out of distribution. So score Jacobian training does this, address this issue by approximating the noisy score with what they propose as perturb and average scoring. And this is different from what is done in SDS. So the idea is to basically first inject some noise to the clean data, and you compute the noisy score model on that noisy data, and then you average the score predictions to get an approximation of the noisy score model on the clean images. So in the right figure, the input blob shows that what they are trying to denoise, and if you directly apply the pre-trained diffusion model on this denoise result, then it will give you a face where the middle blob is of a wrong color, or whereas they show that with their approach, because of they really alleviated the out of distribution effect, you can actually get a better estimate of the denoise result. And again, this different formulation is a competitive alternative to the original Diffusion approach. A final alternative that we want to mention here is a very recent work called Prolific Dreamer. So these SDS-based methods, often they have the problem of setting the classifier guidance weight to very high. And this limits the diversity of the generated samples. However, one very strong fact of prolific dreamer is that they reduced this classifier guidance weight to 7.5, and this also leads to some like quite diverse samples, and you can see here. So under prolific dreamer is this technique called variational score distillation. So instead of trying to directly maximize the likelihood, like under the diffusion model, like variational score distillation or VSD tries to minimize the KL divergence via variational inference. So in this case, different from the original SDS objective, they consider a distribution of nerves, and they try to represent the distribution of nerves with multiple particles. And supposedly, we can draw a sample from this distribution of nerves. Then you can use VSD to simulate this like ODE trajectory, which basically the inner term has two terms. So the second term is the first term is the score of the noisy real images, and this can be approximated with the pre-trained diffusion model on the real images. The second term is on the noisy rendered images, which we don't have right now. So the first part we have. So then the question is, how do we get the noisy rendered images? So the key idea here is that they basically just use the LoRa approach to approximate the score of the noisy render images, because you can get these noisy render images like during this optimization process. You put that into a data set, and then you update your diffusion model with low rank approximation techniques. And in this case, they just did that to like minimize the diffusion loss. And this is basically why it has better performance seemingly than SDS in practice. In the valid text-to-image nerves, they actually form a distribution, and this distribution has like infinite possibilities. So one advantage of VSD is to consider this as a distribution rather than just optimizing one sample. In SDS, the epsilon term, which is basically the noise that we sample, you can consider it as the score of the noisy Dirac distribution or point distribution over the finite renders. And in this case, if you have infinite number of renders, this will converge to this true score. However, in like VSD, they use the LoRa model to sort of directly represent the true score of the noisy distribution. And this potentially acts over like infinite number of renders. If we treat this like mathematically strictly speaking, if your generated nerve distribution only has one point, and your LoRa just overfits to this data distribution perfectly, then VSD is equivalent to SDS. However, outside of the mass, LoRa has a very good generalization, and you can learn from this trajectory of nerve renderings that you optimize. And therefore, by doing low rank optimization, you have better generalization abilities, and therefore it gives you like better like results. So if it's a bit hard to understand, you can think of this as like analogous to if we represent the data score directly on this mixture of Gaussians on the data set, or if we just represent the data set score by like training this unit with LoRa. So if my unit is able to like overfit perfectly, then of course these two are the same, but there is some like, good inductive bias of the unit that actually helps here. So next we are going to talk about diffusion models for view synthesis. So in these cases, you do not generate a 3D object as an output, but you synthesize the view at different angles. So one of the works is called the 3D diffusion. So the idea is that you condition on a frame and you condition on two poses. So one pose is the pose of the one frame that is conditioned. And then you basically try to use the diffusion model to predict the rendering on another frame from a different pose. So the architecture specifically is basically just a unit with two branches, so one branch for each frame, and then these frames are connected by cross attention layers. And to improve the 3D consistency of these methods, they actually use this stochastic conditioning of the sampling. So at step one, so we suppose we start with one view, you use this one view as the like sampling condition for every step. However, after you get like two views now, you want the third view to be consistent with both of the views. So instead, they try to base this on stochastic conditions. So this means that you use a different condition for a different sampling step. So this allows you to cheaply use multiple conditional frames as the information for for sampling, and this prevents you from having like too high memory cost of conditioning on all the frame together. GenVS is another technique that uses a 3D aware architecture with latent feature field. So basically, they first generate this feature field, and then they render it with render like one view of the image using MLPs, and they try to use a diffusion model to like improve the rendering of this particular field. So basically, the diffusion model helps to improve the render quality, whereas there is a underlying 3D structure that is being used to predict like rough high-level shapes. And next, we are going to go talk about 3D reconstruction. So one of the works is called Neuralift 360, and these works are actually quite closely related to the optimization techniques similar to SDS. So in this case, for example, if I want to generate a 3D object from a 2D image, you can actually combine the SDS objective function with different loss functions. So one of them is obviously clip. So if you render this image from different directions, then their clip scores can be similar. And similarly, you can use like depth estimation to obtain like loss on the depths to obtain like a good 3D shape. Another very interesting like method is called 0, 1, 2, 3. So in this case, they first try to train a 2D diffusion model based on like novel view synthesis. So again, this novel view synthesis model tries to get from the input view and give you two poses, and they try to generate the output view with a different pose. And then they would use this new model that is like view aware to run like score Jacobian chaining or score distillation sampling on this technique to optimize the actual like 3D model. Finally, we are going to talk about like 3D editing. So this works called instruct nerf nerves basically converts like a nerf to another nerf, and it tries to edit the 3D scene with text instructions. So for example, you can see in this case, given different text instructions, you can convert the original nerf into different style of 3D objects. So in this case, basically the idea is quite simple. So given the existing scene, suppose that you have already trained a nerf, you basically just use instruct pix to pix that was described in the last section to generate the image at different, edit the image at different viewpoints. So in this case, you just edit the bear image into a grizzly bear. And then after your dataset update, you continue to train the nerf and repeat the above process. So with each iteration, of course, originally these views are not going to be like consistent with each other because there will be slight differences. But with with this iteration going on, because we always train a nerf with the 3D underlying structure, these edits will become like more consistent like as the training goes along. And I'll skip to this one, but again, this is basically mostly based on the score distillation sampling techniques with the text guided image diffusion model. And next time, I'm going to talk about video models. Most video models are trying to lift existing image models to a video model to contain the temporal information. And one of the primary reasons is that image models are available, and video models are very expensive to train, and we don't have that much video data. So the first work on this that I know of called video diffusion models tries to get a 3D unit and from a 2D unit. The idea is as follows. So basically, the convolution layers stay the same, but the attention layers were changed. So before there was only like spatial self-attention layers, but now because we have to consider the temporal information, so they also factorize this temporal information after temporal attention after the spatial attention. So they basically have a factorized spatial and temporal attentions, or this temporal attention could also be implemented as a convolution. Image and video takes this to another level. So basically, they train this very large-scale text-to-image video model, which has like 7 cascaded models. So from the input text prompt, they first process the text embeddings using T5, and then they have like 7 different models for like getting a high-resolution video. So they have a base model that acts on a very low-resolution image or video clip, and then they have like 3 temporal super resolution models and 3 spatial super resolution models, and these can be trained independently. Make a video is slightly different because they try to train, also try to lift an image, text to image model to a text to video model, but they don't want to train on like text to video pairs. Again, this is similar to the existing frameworks that they're trying to do a lot of like frame interpolation, spatial or spatial temporal super resolution. But what is different from image and video is that they also consider doing approximating a 3D convolution by factorizing the convolution into a 2D spatial convolution and 1D temporal convolution. The way that the 3D attention is obtained is similar. There is a spatial attention followed by a temporal attention. And video latent diffusion models is again similar, as now you guys would know that this basically tries to fine-tune a text-to-video model from the text-to-image model. But there are also some notable differences from prior works. So first of all, this acts on the latent space. And even though it's possible to use the same like image latent model on each frame, they actually try to fine-tune the decoder model over a video-aware discriminator. So the encoder fixed, but the decoder was trained on like video data. And next, this fine-tuning approach again tries to add temporal layers, but instead of adding 2D and 1D layers, they actually consider like 3D convolutional layers. So this is an actual 3D convolutional layer, which is slower in terms of compute and like worse in terms of memory, but it might capture like more complex interactions in this 3D case. And again, they have like a 5-stage pipeline where they first start from like a lower resolution, a latent frame video diffusion model, and then they try to do like latent frame interpolation, decode it to pixel space, and then apply like optionally video upsampler. So next, we're going to talk about some like video style transfer and editing methods. The first I'm talk about is Runway ML's Gen 1. So the high level idea is that they want to transfer the style of a video using text prompts given this driving video. So basically the driving video is just the existing video. So for example, we can see on the top row here, a person is using a laptop in this inside a train. But the prompt now specifies that this is the anime style. So Gen 1 basically tries to transfer the style of the video with this driving video and the text prompt. So the idea is to basically condition on two things. So one is the structure given by the driving video. So basically you can get some kind of structure using depth estimators. And then you also condition on the style or the content, which can be given as like clip information. So during the training, they basically try to use depth maps and use that as a conditioning information for the diffusion model. And this diffusion model currently acts in the latent space. This is basically the depth information is concatenated with the latent space. And clip image embeddings are also provided via like cross attention blocks, where it produces the like text related information or like style related information. So during inference, it takes a different approach where it still conditions on the text, on the depth of the driving video. But because we want to change the style actually comes from the clip text embedding. And there's a model that tries to convert the clip text embedding to the clip image embedding. And then these are just placed into the model during like inference stage. Next is the work called Pix2Video, which basically just try to do video editing, but without a video model. It's only based on the image diffusion model. So here, the idea is to try to edit, video given a sequence of frames. While it's possible to do something like image editing on each individual frames, like prompt to prompt, this will actually fail to preserve the temporal information. So if you look at this, this will actually give you very inconsistent frames that that is like very noisy. So so these results are not great. So what did Pix2Video do to improve upon that? So first thing they did was that they tried to do self-attention injection. So first of all, they tried to use DDM inversion to invert each frame to a particular time step. And then in order to make sure that the two close frames are like giving you similar results, they basically try to use self-attention features from the previous frame to help with that. So more concretely, in this figure, basically the query of the attention layers are from this current frame I, but the key and value features are given from the previous frame. So basically you use the key and values from the previous frame and the queries from the current frame to get the output of the self-attention layer for the current frame. So in this case, you sort of have some kind of a consistency between the different frames by injecting this attention information. The next thing they did was that they do this reconstruction guidance for the latent space update. So the idea is that they want the latent space of this frame to be relatively close to that of the previous frame. So basically you can do that by adding a loss function and optimizing that. And this tries to encourage that the two consecutive frames look quite similar. And with these two methods, you actually improve the temporal consistency of the final video. So as you can see here, instead of getting the very random frames, you actually get relatively consistent frames across the video with a similar style. I have to know that this field is very hot, and there is a lot of concurrent and related works on this topic. So for example, in video P2P, basically they do prompt and prompt tuning with a text-to-video model. And this is basically similar to how a prompt-to-prompt is done with a text-to-image model. And in phase 0, they also do DDIM inversion, but they additionally use information from the attention maps of the DDIM inversion and save it for later use. In tuna video, they basically try to fine-tune a text-to-image model to a text-to-video model by fine-tuning certain projection matrices of the attention layers. And in Vid2Vid0, they basically try to do something, learn a no-text embedding similar to how texture inversion does. And last but not least, we're going to cover some parts on diffusion models for large contents, as well as some safety and limitation concerns for diffusion models. So generating large contents is actually of interest. So before there was works like SignGAN or GAN methods that tries to generate a very long or large images. And can we do the same for diffusion models? It turns out that we can. So we can always try to do outpainting, for instance. So for example, let's try to generate this very long image with the diffusion model. But let's suppose that we can only train our diffusion model on the square regions. The reason why we cannot train on this bigger region is because that the memory cost will be too high, and there's not enough data sets, data points in the data set for us to train on this type of data. So an outpainting solution will work as follows. So first, we will generate the center region. And let's say this region, I split it into left called X1 and right called X2. And then the outpainting method will basically condition on the X2 to generate a new part to the right, which is X3. So now by doing this conditional sampling in a nearly autoregressive manner, I can increase the size of the image. And by repeating this, I can make the image bigger and bigger. However, this has a problem in the sense that it's not very efficient. So on top of the number of steps you have to take in diffusion models, you also need to scale the linearly with the content size. So if my image is very, very long, then the latency will be super high. What's very interesting in diffusion models, other than autoregressive models, is that unlike autoregressive models, you can actually use diffusion models to generate these very large contents in parallel. So therefore, you can just avoid all these issues that you would encounter in autoregressive models. So for example, what you could do is we sort of reformulate our previous formulation for outpainting. So in the previous formulation for outpainting, we have a conditional independence assumption. So conditional X2, X1, and X3 are independent. So we can basically sort of rewrite the joint probability of these three variables into first this factorization. The first factorization is X1, X2, and then there's Q X3 given X2. And you can basically just apply this definition of a conditional probability to get this division. So you have the probability of X1, X2 times the one of X2, X3 divided by that of X2. And if you take the log of that, you would get the sum of these cases. So you have the log probability on the two of the larger pieces summed together minus the log probability of the piece that is overlapped. So we can call the larger pieces the factor nodes, and we can call the smaller pieces a variable node in the factor graphs, factor in the probabilistic graphical model literature. So these taking the derivative of these, we'll just get the scores of these. And these, because diffusion models are very closely connected to score functions, these scores can just be run in parallel with the diffusion model. So concretely, we can construct a large diffusion model working on a large piece of content just by combining diffusion models working on the small pieces of content. Again, more specifically here, we have this slightly longer image on five parts. So we're going to just split it into like 5 different pieces with 3 vector nodes and 2 variable nodes. We're going to run this diffusion model in parallel in each of the separate regions. And then we are just going to sum and minus the intermediate pieces to obtain the final output of the diffusion model. And this does not have to be limited to like a simple linear chain graph, as we show in this case. You can actually easily connect this with a cycle graph in case you want to generate 360-degree panorama images. You can extend this to grid graphs where you can do like longer images, or you can extend this to 360-degree like cube map graphs to generate like entirely 360-degree images. So this is quite extensible, and you can all generate these in parallel given enough memory. So one obvious application we can do is like long images we showed earlier. And we can also use this to extend the capabilities of a motion diffusion model. So for example, here we try to generate a looped motion with a different text prompt that are concatenated together. And if you try to do this with a regular motion diffusion model, it will fail miserably because the motion model has never been trained on like very long sequences. So the self-attention mechanism will kind of fail. And of course, these ideas could also be extended to video generation if you want to generate like longer sequences of video. I have to know that similar ideas also appeared in the literature as well, and they sort of based on similar ideas, but they kind of differ in terms of how the overlapping regions are mixed. So finally, we're going to talk about some safety and limitations of diffusion models. One first limitation of the diffusion model is data memorization. So because the diffusion model is trained by a maximum likelihood objective function, it has the tendency to, quote, memorize data. So for example, on the left image, we show like the image from the training set with this particular prompt for this celebrity. And you can actually use this prompt exactly to reproduce the image from the training set from the celebrity. So this doesn't happen all the time, but the fact that it happens shows that the diffusion model can memorize data. And the same authors also try to evaluate these properties with GANs, and they find out that if your model, like with the diffusion model and the GAN model, if they have the same FID as a measurement for image quality, the diffusion model can memorize like more images in the data set compared to the GAN ones. Nevertheless, if your data set is big enough, then this memorization issue is not that obvious, and you oftentimes the memorization happens if you have a lot of duplicates in your data set. And for example, in the line data set, there can be like duplicates up to like hundreds of the same image. Nevertheless, like deep duplication is a way to like help alleviate this problem, and there's also an ongoing like active work of research on how to reduce the memorization in diffusion models. Lastly, we're going to talk about how you can like erase certain concepts in diffusion models. So for example, I want to, there might be copyright issues in terms of some figures in the images in the data set. So for example, I want to erase a certain artistic style to not have copyright issues. Or I want to erase like certain objects in the diffusion model or this certain concept. So in this case, the authors propose a method that basically tries to, fine-tune existing text-to-image model, and the way they do this is basically that they want to use classifier-free guidance, but in the opposite direction. So basically, they use this negative classifier-free guidance, whereas before you use a positive guidance weight, now you use a negative guidance weight. So it reduces the probability of generating the concept or an object in this new diffusion model. And again, the new diffusion model is fine-tuned from this new score function. And basically, it won't affect like existing like concept that much because the new scores weren't changed. But for a concept that you care about removing, it is effective at removing these kind of concepts. So this is very important for like cases where you want to remove certain concepts in diffusion models for copyright issues. So yeah. we covered a lot of topics, and in the first section, Arash covered mostly about the fundamentals. And in the second section, Chen-Li mostly covered applications on images. And in this final section, I covered mostly on the applications that are derived from images, but on different domains, such as 3D and video. And again, we have to admit that there's a lot of very good papers on the topic, but we can only cover like a few of them. And we, again, thank the community effort to give us a curated list of papers. And if you're interested, you can go to this GitHub page to see who contributed what and the list of papers. And the slides and the recording of the tutorial will be available at this webpage. And we also have the barcode for that. So yeah, thanks everyone for your attention. And finally, we will show a list of contributed papers to this repository. These are the ones for the first part. These are the ones for the second part. And then these are the ones for the third part. So they will be also shared. So yeah, thank you. And any questions? Yeah.
One challenge for video generation is how to generate for a long video, which can get lots of challenges for